Now I think we are live on YouTube also. You have all the titles and everything and information about the speakers, right?
Oh, me?
Yeah.
Yeah, I have, yeah.
Okay, good. Swankar, you do not have a WhatsApp number? You're not using WhatsApp? Swankar?
Good.
Hello. You have to unmute.
Good morning, Didi. Good
Can you
morning.
hear me?
Yes.
Okay. No, I'm telling Shubhankar that
Didi, I can hear you.
so you see me maybe logging in and out often. Okay, so I just wanted to keep you informed. Because since last night my internet went down,
Okay.
I put in a complaint, but it hasn't come back in.
Okay.
Anyway, I'll remain, but I may get spontaneously logged out a couple of times.
Okay.
Vivek, I sent you this PDF file of Professor Sampath Kumar answer.
Okay, fine. Okay. Professor T.V. Ramakrishnan is here.
Good morning.
Good morning. Hello. Good morning. Good morning.
Good morning, Professor TVR.
Hello, good morning.
How are you?
All right, vertical.
Professor Mahajan, good morning.
Hi, good morning.
Good
Hello,
morning, Professor Mahanti.
Hello. Hi,
Hello.
TVR. Hi.
Hello,
everybody.
Professor.
Nice
Good
to see you,
morning.
TV. Good morning. Good
Good
evening.
morning.
It's morning there or not, but it is morning here.
Yeah, I know. You are good. 9 o'clock there. It's 7:30 evening in Los Angeles.
Not too bad.
Not too bad. Actually, it's a little late in Michigan, but I'm in LA. Hi, Tulika.
Hello, Professor Manti. Hello.
Nice to see you.
Yeah, thank you. Nice to see you too.
Good morning, Vivek and Shivankar. Good morning, Professor Mahan.
Good morning. Good morning, Sachin.
Good morning.
If you are in Bangalore or in Banaras?
Bangalore.
Bangalore.
I've been in Bangalore for almost 2.5 years, 3 years. Yeah.
Okay. Yeah, I knew that. It's just
I mean, totally in Bangalore.
so mostly you are staying in Bangalore now?
In Bangalore only.
Okay.
Namaste, Yogesh ji.
टीवीआर जी नमस्कार।
नमस्कार, नमस्कार। कैसे हैं?
ठीक हूँ आप?
बस चल रहा है।
Okay. So how is your health now? I had heard.
So I'm health is all right. I mean, so far, as I said, I am vertical.
You look good.
So sense of humor is intact. Good. That is always a good sign.
Hi, Deba.
So maybe we should also wait for a few minutes and then, because still participants are joining. So let's wait for a few minutes and then we'll start.
Good morning, Kaloda.
Good morning.
Good morning.
Indra, good morning.
Good morning, sir.
Hi, Carlo.
Hi, good morning. Good morning to you all.
Good morning.
Very
Good
nice.
morning.
Didi is also here, but he already said that he is having terrible internet connection, but he is there. I'm not sure if he can listen to us or not.
Well, his name is here now.
Yeah, he is there, but he has a very bad internet connection. His internet, he's doing from mobile phone only.
Achha.
I can hear you. I can hear you saying all the things. The only thing is that when I speak, it will not come through very clearly.
देखिए, we didn't say anything bad and we won't, even if you are not hearing.
हाँ बताइए. No. I'm listening. I'm listening. Well, I'm just saying that I'm there.
Yeah,
but
good.
It's in a very bad. Last night चला गया after the बारिश हुआ ना कल रात को बहुत जोर से.
हाँ.
उसके बाद इंटरनेट चला गया था घर का तो मोबाइल.
अब देखिए पानी यहाँ नहीं ठहरा है इसलिए इंटरनेट चल रहा
लगा
है.
दिया मैंने. So because this morning session is very interesting. I'm going to be there too. टीवीए जी आप आ रहे हैं ऑफिस को या you had said that you are coming a few days per week, right?
I come very often, maybe 2-3 times a week, which is considered often. Now Hassan is also here, and I'm doing something with him. So maybe today or maybe Monday I'll be there definitely.
Okay. And it
Morning.
looks like next month maybe vaccination will also begin.
हाँ मैं उसके पीछे पड़ा हूँ लेकिन कुछ पता नहीं चल रहा मुझको.
So maybe I think we should start.
Yeah.
Okay. Good morning, everyone. Very warm welcome to all of you in this Professor S.K. Joshi Memorial Session. Today we have privileged to have Professor T.V. Ramakrishnan as a chair of this session. First, he will speak. He will give an introductory talk about Professor Joshi's work, and I request Professor Tulika Maitra to coordinate with him during this session about the sharing the screen and so on about his talk. So, Professor Ramakrishnan, please. Yeah.
Fine. Thank you very much. It's I don't know what to say, whether it's a privilege or honor or a sad duty to talk about Professor Joshi. I have known him for, I don't know, since 1975 or so. So it's a long association, both professional and personal. and I will share some of it with you just now. And I'm very glad that many of the people who actually worked with him and were in the physics world of India at the same time as him, and also interacted with him like Bhanu Mohanty. They all talk about him. So it's a very great and I think unique occasion. I will start by trying to share my slides, which I prepared for this occasion. Let me click the right button. I hope the right thing happens. Nothing has happened.
Shall I start sharing? Shall I share your slides for you?
I will just 1 minute. Yeah, you can do that also. You can do that also. Yeah. So now I'm there, and presumably I'm sharing. I don't know. Maybe Philipkarji will help. And what is it? Okay. Yes. I don't know whether you can see this.
We can see it.
But I have started with his full name, Professor Sri Krishna Joshi, also known as Professor S.K. Joshi, and to most of us as Joshi Ji. There is a picture of him taken maybe not too long ago, maybe a few years ago, which shows one very well-known characteristic of him, that what is called Mandasmita in Hindi. It is just a mild smile of goodness and characteristic smile of goodness which cannot be faked. So I'm really very happy that friends who knew him are expressing themselves. I will start with the bare bones of his life, just a sort of elementary, basic, factual introduction to the progression of his life in this world. Joshiji was born in 1935 in a village in Champawat district, which was then in UP and now it is in Uttarakhand. He studied till his BSc in that area. He walked to school for several miles, and that made him, of course, quite tough and also gave him a lifelong love for walking. He then moved to Allahabad University, where he did his BSc, MSc, and also his PhD. And his PhD thesis was with Professor Kedareshwar Banerjee, who actually was a pioneer in the theory of direct scattering theory of X-rays. And the thesis, Professor Joshi's thesis, is on diffuse X-ray scattering from organic molecules. But interestingly, though he was really very dedicated to Professor Banerjee, actually he went to IACS Calcutta when Professor Banerjee retired from Allahabad and completed his PhD in Calcutta. Professor Joshi struck out on his own even as a student and started working on lattice dynamics of metals, on force constant models for lattice dynamics of metals. And this field, which is actually quite popular at that time, he brought his characteristic originality and energy. He was totally self-made. And in this field, over a period of 5 years, both as a student and then as a young lecturer, by himself and with his collaborators, he published about 50 papers on the subject in about 5 years. This is considered quite large for a physicist. He was then in 65 to 67 a visiting assistant professor in UC Riverside as a physicist, which was actually quite a transformative period for him. He then joined the Roorkee University, which actually is the child of the Thomson College of civil engineering, which was founded, I think, in 1837 or so, and is actually the forerunner of the present IIT Roorkee. So at that time, it was a provincial university. He was made a professor there, a very young professor at 32, and he was there from 1967 to 1986, which is about 19 or 20 years. Then he became the director of a National Physical Laboratory in New Delhi from 1986 to 1991, about a 5-year period. He became then the Director General of the CSIR, Council of Scientific and Industrial Research, in 1991, and he was the Director General in 1995. After retirement, he was in NPL as a scientist till 2020 when he passed away. So that is, I think, the bare bones. My interaction with him started and became strong during his Roorkee period. When I came to know him, many of his students like M.M. Pant, M.P. Das, and so on, and his associates like Deepak Kumar. It is a well-known fact, or at least a fact well-known to people of a certain age group, that Professor Joshi transformed physics in Roorkee by his example, his transformation of the education in physics there, MSc education, through additions to the faculty, and actually made it one of the leading research departments, physics departments in the country. And the amazing thing, which we don't quite appreciate, is that he did all of this in a provincial university with all its constraints. This did not embitter him. He was quite successful in doing that, and he worked within its constraints. He then started, in this period, he started research in areas which are completely new to him, such as electronic behavior of disordered systems, physics of strong correlations, atomic physics, and so on. He was a very hard-working physicist. He regularly spent 14 hours a day in the department, thinking, reading, writing, discussing, and learning from students and colleagues. M.P. Das, an old student of his from that period, told me of this classic exchange. A professor of the Roorkee University asked Joshi ji, Professor Joshi, you have done research and got your PhD. Why are you spending so much time in the department? Professor Joshi said, my student friends are doing much harder work. I want to know more about modern solid-state physics from their work. He was one of the interesting characteristics about him was that he was genuinely non-hierarchical. And this is quite unusual in almost anyone, and especially unusual in people coming from his more or less traditional background. For example, M.M. Pant, another early student, he tells me of an event when he was a PhD student, and he and Joshi ji were to present their results at a conference. Of course, Professor Joshi was billed as a speaker. Joshi ji insisted that not only should Pant present this work, but he should also get the credit for it. The other thing which I found quite remarkable about Professor Joshi professionally is that he could sense the coming of computational science in physics. This was in a period when computing was a real pain. At that time, well, many things which one could talk about. But for example, the Roorkee University had a very slow, primitive, gigantic computer, which was actually of almost no use to them. So his students had to park themselves in the few favored institutions like TFR or IIT Kanpur for weeks and months to get bits of computer time. He himself had a lot of trouble mastering Fortran. He wanted his students not to be handicapped by all this and made sure that they became proficient in the field. So this he did by maybe they spent time in Trieste or in Waterloo or wherever it was possible, but they should be at home in computing. This is an old era because Today, even a laptop, which everyone has, is obviously much more powerful than those gigantic computers. In this period, he rose to national prominence. His gentle but academically and professionally perceptive personality meant that he was much in demand in Delhi for various national meetings, selection committees all over the country, and so on. And he took this also in his stride. In those days, you see, if you had to go from Roorkee to Delhi, well, you had to take a rickety government bus. Now, Professor Joshi wanted to go and come back the same day and do physics after that. If you were tough enough, you could do it. You have to start at 5 in the morning. He did that very often. And after that, he had a long session of physics discussion with a fresh mind with his students. Now, that was I think that was the most important, in my view, the most important period of Professor Joshi's life, formative period. Then, of course, he became a national figure in science as the director of the National Physical Laboratory and then as the Director General of CSIR. The Director Generalship of CSIR came at a very interesting time. You see, just about 3 months before he became the Director General, economic liberalization had been not only announced, but it had started. And this had a very big impact on the CSIR laboratories. Till that time, these laboratories were highly cocooned and protected, well equipped, were generally quite inhomogeneous in quality. But they had to very quickly become industry-friendly sources of innovation, market their science and technology base, compete in the open, and become self-supporting. This was a tough challenge. He met it by first preparing a detailed plan, by first having an advisory committee which is powerful and knowledgeable, consisting of many CSIR laboratory directors and others who could do something. Then they prepared a detailed plan, which was for the entire CSIR and also for each laboratory, giving a kind of a roadmap of what they should do to reinvent themselves and stay relevant in this competitive, open, and unprotected environment. This period, though very important, lasted for a few years. He retired, but all through that period and later, he contributed crucially to the strength of physics, the quality and diversity of physics in India through his leadership and participation in a large number of committees. And it became a joke to say that, oh, this is a Joshi committee. But it is not, you see, it is not because he was just a kind of item, innocuous, vacuous, a good appendage, but because he genuinely listened to people, he was gentle, he did not judge people with a lot of prejudice, but one could be sure that his academic values were not elastic. They did not change. They were very much there, and also because he had a very deep knowledge of ground realities. His personal beliefs were, he grew up. He was a child of the Himalayas. He was personally very religious, and observant, but he did not allow these to influence his professional life, professional acts, what he did, what he expected of people professionally, and so on. It is not that he was a light hidden under a bushel. He was actually widely recognized by the scientific community in India. He was awarded the Bhatnagar Prize in Physical Sciences rather early in 1972. He was a fellow of all the 3 national science academies. He was a fellow of the Third World Academy of Sciences, and he was the president of Indian National Science Academy for a term. I feel overall that though it's a great personal loss to many of us, it's a great good fortune for us as a scientific community that such a leader who combined in him great personal qualities of hard work, scientific ability, and effective leadership was amongst us at this time. That's all I wanted to say, but I think people who knew him in different aspects of it, I hope they will say more. Thank you very much. Yeah, I'm sort of restarting.
Hello.
I don't know what is happening. I'm hearing a
There is noise
loud noise of some sort.
and your screen has many images.
Hello, Professor Ramakrishnan. I think your screen is still shared. Well, you have to stop sharing from somewhere.
And of course, but that seems to start off another round of.
It's leading to an infinite regression, some kind of a loop.
Right.
Okay, I will start. I will issue.
Namaskar, Professor Ramakrishnan ji. This is Alok. I think probably what is happening is that you're trying to have two parallel WebEx sessions, which may not be possible. You may have to log out from one and join the other.
Okay. I'm not. So maybe I should. Okay, I will just start from the very beginning then.
So TVR, you can hit the red cross and then join again.
Yeah, I'm doing that, but I'm getting a whole. Sorry. I'm getting a whole tower of things.
This is really lovely.
Okay.
This is complete infinite regression displayed on.
Okay, doesn't matter.
Can the organizers log him out and then he can log back in? I think that is the best way.
Yeah, that may be a good idea.
Okay, that's what we can do. You please log in again. I will log you out. Yeah.
That was clearly a non-converging infinite series.
Something of that kind must have happened.
Possibly.
Yeah.
Yeah. Multiple sessions and the same sound is being fed back, no?
Yeah.
Echoing, yeah.
But this is the first time I'm saying it. I've seen the audio loop back, but the video loop back wasn't new for me.
Shall we continue with, with the session, or shall we wait for Professor Ramakrishnan to join?
No, I think he has to chair now, so we need to wait for that to work.
Okay.
I think it will be done soon.
Hello, Professor Ramakrishnan, you are muted, I guess. You have to unmute.
Yeah, unmuted. And now things look more normal. Yes.
Yeah.
Thank you. Yeah, I'm done actually, but I think I don't know who the next speaker was, but maybe you could.
Yeah, next speaker is Professor Sampath Kumaran.
But TVR, I think you are the chair of the session, so maybe you.
Yeah, I'm the chair, but I'm the ignorant chair. I don't know who the speakers are, and I don't see Sampath Kumaran.
I'm here.
You're here. Oh, good.
Good morning.
So go ahead. Yeah.
Okay, can I start?
And maybe Tulika can keep the time to help TVR.
Okay.
Yeah.
Okay, I'm starting now.
Please.
I'm sharing the screen. Oh, what do I do? You have to. Oh, I shared the screen. Can you see?
Something is starting to happen. Yeah.
Got it? Got it?
Yeah.
Yes, sir.
We can see your screen, yes.
You can, okay.
But it's very tiny.
Okay.
At the moment, it is tiny.
It's very strange.
Okay,
it's okay.
Okay?
Almost full.
Okay,
Part
thank
of
you.
it is. Yeah.
Okay. Good morning to everybody. First of all, I would like to thank the organizers for inviting me to give a talk in memory of Professor Joshi. As Professor TVR said, I don't know whether one should feel happy about it. It's really a very sad occasion and to sort of give a talk. I mean, I wish that he's alive and then we give the talk, but unfortunately he's no more. Professor, before I actually begin my technical part, I would like to say a few remarks, if I am permitted. And Professor TVR already very beautifully brought out the qualities of Professor Joshi. And I had some interaction with him. Of course, I knew him for the past more than 4 decades. And he is one person, irrespective, as Professor TVR pointed, irrespective of age, he always used to respect everybody around. As a very young graduate student, used to treat in a very such a humble man. He will come down to our level and talk and anything from science on everything. And the second point is that he is a great admirer of experimental data. I mean, he loves to talk to experimental data, like for example, TVR. There are a sort of people who can talk about to experimental, come down to the level and discuss the data rather than going too deep into the theoretical aspects while discussion. I remember he gave a talk 10 years ago in an MRSI meeting, an inaugural session. He was supposed to give a status of the material science in the world. I was very impressed that he gave such a very beautiful summary of current status at that time in material science. What I met and told him, he was not even a single equation, no theory, nothing, purely materials physics. I mean, coming from a very strong theoretical physics background, somebody giving a talk, very beautiful review, it was something very great, very admirable. That tells you that the person really keeps track of the literature from time to time and try to see, contribute how best he can contribute to the society. He is basically a very, very serious person. And as I said, he is a very thorough gentleman and a man of great personal qualities. And something it's a pity that we have lost such a great person. I remember that 1 month before his demise, he had some correspondence with me on some occasion, on some matters. And I could never imagine that he was ill. Apparently, while later on I came to know he was actually seriously ill. And afterwards, he passed away. What I want to tell you that he was here holding various positions till last minute in various institutions, governance council chairman and various other things. Till last minute, he was active. He wrote to me some mail in his capacity as governing council of some institution. So that shows the person is very, very serious till last minute. I mean, it's really a great loss for all of us to have. We have lost a great leader. Anyway, so today I'm going to choose a title talk which normally will not talk about, that is about gadolinium alloys. Gadolinium is most uninteresting element in the periodic table. And I will soon come to you why I've chosen this. I've been working on different kinds of phenomena like spin chain phenomena, geometrical frustration, multiferrize, quantum physics, heavy fermion, things like that. I'm very excited to talk about, but I decided to talk about this. The reason is, soon I will come to that. The first reason is that, the field of strongly correlated system is now more than 5 decades old. And at that time, it's true even now, that there were difficulties in understanding the experimental data even qualitatively. Very difficult to draw systematics. And I thought at that time that one should move away from strongly correlated systems. Of course, I was studying those systems like cerium and ytterbium and europium and transition metal, things like that. But I should look at somewhat simple systems and see whether we are missing something in quantum physics. And I started with gadolinium. Gadolinium is the least interesting element in the periodic table from the magnetism angle, also from superconductivity angle. So I started looking at it. I found some anomalies in 1995. I have a series of papers in Physics Review B and things like that with my students. And by the way, I listed my students and postdocs here. And many of them are employed very reputed institutions in the country. And I also collaborated with a larger number of people outside to carry out photon emission, to have neutron diffraction, ESR, and various other measurements. And I'm not listing on all these colleagues here. This is going to basically brief you a review from 1998 to 2020. We started with something very ordinary material, which nobody has studied in the past, and brought out something exotic, and it was not understood for 2 decades. Now there's sudden interest now in the recent literature. I thought I should brief you about what was the original result and what is interesting thing now. That's what I will do. A very, very modest aim. Again, I'm not going to talk about all the experimental results from various techniques. I'm going to focus only on the electrical transport, which every student can really understand, not going too much of detail. Electrical test is like a blood test. If somebody measures electrical resistance of material, you will come to a problem with the material. Then you do other things. I will bring out only the electrical resistivity data, not other things. This is the first aim, basically, to address whether there is anything we are missing in the transport phenomena of solids. Look at simple material and bring out the complexity of the solid state physics. The second reason is that there was Professor TVR probably would recall that there was a felicitation for Professor S.K. Joshi in IISc Bangalore, organized by H.R. Krishnamurthy, Sriram Sastry, probably also Rahul Pandit. Professor TVR was there, Srinara, all these people were there. I was honored to, I was invited to give a talk there. I was very much honored. And I gave a talk, the topic of the conference was correlated systems and quantum materials. held during September 14th to 16th IISc Bangalore. I talked about the topic, exactly same topic, unexpected transport behavior of gadolinium alloys. Okay, just I given the same title. This is in honor of Professor Joshi. I am sure you would be very happy. So in fact, recently had a correspondence on this with me. Therefore, I should choose that, bring it out. Exactly same topic I'm going to give you, bring out the initial results and then where we stand today, the most recent results. That's what I will do. So basically, I'm just picking this topic for this particular reason. Okay, this for the benefit of some students who are in the beginning of their career, just 5-6 concepts will be very, very elementary. Please pardon, experts should pardon me. And whereas, you know, we go from lanthanum to lutetium, what is really varying is essentially the 4f electron count. It was believed for a very long time that the 4f orbitals are strictly localized and just doing the radial distribution function as a function of the distance from the nucleus. You could see the 4f orbital is very much deeply localized compared to 5s and 5p, which are essentially outermost orbital in a rare earth ion. Of course, the d electron, 6 electron participate in bonding. So it was believed for quite a long time that the 4f orbital cannot participate in bonding. And now it is recognized. During 4 decades ago, the carried out, it is now generally accepted. There is enough evidence today that this is no more not true when it comes to light rare earths like cerium, to some extent also praseodymium and iridium. But there is some degree of delocalization because of which a whole lot of phenomena you find in solid state materials. However, now it's accepted that this problem does not exist when it comes to middle of the series, like gadolinium, terbium, dysprosium, holmium, erbium. It is now believed that for the orbital very, very deeply localized. Therefore, you don't expect any great anomaly due to 4f electron delocalization or any other phenomenon which is of great current interest, barring some magnetism aspect. Okay, so therefore the event that 4f electrons are strictly localized, your very, very famous factor called de Jones factor, you can really we call Gj minus 1, G is the Landis factor, and J is a total orbital momentum. You can derive a parameter called de Jones factor. It is expected that all the properties, many of the properties like magnetic ordering temperature or spin disorder resistivity, some of these things are expected to scale to this factor. In order, if you know the number for one, you can predict what the number should be the other. So this often breaks down the beginning of the rarest series because, as I already mentioned, there is some degree of 4f electron delocalization. So therefore, kindly remember this particular factor in my talk. Okay, now let me come back to the electrical transport, which is going to be the main data which I'm going to emphasize. If we take a rare earth material, a normal rare earth material, when I said normal, as I already said, where we don't have 4f electron delocalization effects, simple like material gadolinium, you have 3 contributions basically for electrical transport. One is that residual resistivity, and then phonon background, which is coefficient is temperature is positive, and then a spin disorder contribution in the paramagnetic state, which is supposed to be constant in the paramagnetic state. At the magnetic ordering, you are losing it because the loss of spin disorder contribution is dropping at the magnetic ordering temperature. If you add up these 3, this is what you get here. So these are normal behavior. So if you apply a magnetic field and measure magnetoresistance, under this number is expected to scale with the de Jones factor I already mentioned. This is for a strictly localized case. If you take, therefore, you apply magnetic field, measure magnetoresistance, you will find in the paramagnetic state, in the paramagnetic state, you will not see any virtually very little effect on the electrical transport. Therefore, magnetoresistance is much, much less than 1. Of course, magnetical orders can be a bit more complicated depending upon the nature of magnetic structure, which I will not talk about. Therefore, if you measure as a function of field, I'm showing some examples here. Magnetoresistance as a function of temperature for the field which you can apply in your laboratory, typically 16 Tesla or 20 Tesla, you will not see any change in the electrical resistance. I'm just showing the experimental measured data here for some material. This is supposed to be the normal behavior. Okay. Now, in contrast to that, if you come to light rare earths, for example, cerium, you have additional interaction. Till now, I talk about the simple magnetic ordering arising from the indirect exchange interaction, that is RKKY, which mediates magnetic ordering. However, you have on-site interaction, which is called Kondo interaction, which is a which have spin flip contribution at very low temperature, below a characteristic temperature called Kondo temperature. you are forming a singlet state because of which you are losing magnetism. So basically, you are getting enhanced polyferromagnetism. These are on-site interaction. And this functional form, it goes exponentially with the exchange interaction strength, whereas RKKV goes like J square. Functional forms are different. So therefore, you know, the well-known Kondo effect first observed for iron impurities in copper, you could see there instead of seeing a normal copper-like behavior using additional contribution at low temperature, which is varying logarithmically with temperature, this is called the Kondo effect. In other words, Kondo effect is defined by a system in which your electroresistivity exhibits a minimum in its temperature dependence. So this is a typical behavior of Kondo effect, which varies exponentially as function of exchange fraction strength. Now, when you come to rare earths, it was believed 4 decades ago or 5 decades ago, it is in principle you can have Kondo effect in a concentrated system, and that is at every site you can have Kondo effect. And therefore, because the reason is that it was believed that 4 of orbitals do not overlap at our 2 different sites, which is not the case in the complete transition metal system. The significant overlap, therefore, you cannot have Kondo effect on a concentrated lattice of transition metal. In general, there are some exceptions for that. But in general, you can expect Kondo effect every site. Therefore, it is called Kondo lattices. Because of this interaction or on-site interaction, which essentially due to some degree of 4 of delocalization, you have enhanced density of cell film level, there's a renormalization of density of states, the even heat capacity goes up, the linear term at low temperature goes up. Therefore, they're called heavy. They are also heavy fermions. Okay. Therefore, if you take a concentrated system like, for example, cerium metal or cerium aluminium 2 or compound, you have 2 interactions. One is the on-site interaction, which is Kondo effect, goes exponentially with the exchange interaction, and whereas also intersite interaction, which is promotes magnetic ordering. One is killing magnetic ordering, other one is promoting magnetic ordering, which goes like a square of the function. Then these two will compete depending upon the strength of each of the interaction. One can dominate over the other. In any case, if you look at the electrical resistivity as a function of temperature, over and above the minimum, you sometimes Kondo lattices, you will have a drop because of coherent scattering, which I will not go into detail now. But this drop is all the signature of a magnetic ordering at temperature. You know, if we take a magnetic ordering Kondo lattice, that where RKKV dominates over Kondo effect, this is a typical feature which you expect here. Therefore, please, I request students remember that this is the typical feature of magnetically, for a Kondo lattice where you have magnetic ground state, where magnetic ordering is the dominant one. Okay, therefore, under the assumption, the story was built for quite a long time, till 2000. I would say that any upturn at low temperature was attributed to Kondo effect, particularly around 1990 to 94, upturn was seen. It was not logarithmic function. It was essential about the linear function here, and people attribute non-fermi-liquid behavior, and therefore most of the upturns at low temperature was attributed non-fermi-liquid behavior even in Kondo systems, and that created a lot of mess in the literature that time. So now, when you come to gadolinium compound, what we have done is, as I already mentioned, that look at somewhat simple system where you don't expect Kondo effect. You know, the case of gadolinium, you don't expect Kondo effect. The main reason is that 4 of orbital is strictly localized. The energy position refers to Fermi level is few electrons below the Fermi level. There will no very little scope for that electron come out to go to conduction band, come back, or to hybridize. Therefore, this interaction is virtually negligible. Therefore, you don't expect the kind of features except for cerium compound. Now, what we found, some of the materials which we were studying in 1996, that instead of seeing this behavior, we found there is a significant magnetoresistance of some of the material. I listed down here some of them, and there is a significant change in the electrical resistance function of as a field, and this raises a question to us whether there is any extra contribution coming up here. So therefore, in other words, subtract the lattice part, you see a Kondo-like minimum here, but it doesn't go logarithmically in the system. Therefore, then we thought, okay, why not study more compounds and try to see. We studied some other compound, and this is the. I'll show you I pick up only one example and well more time on it. And there are many examples. I will flash them now. The most famous example is DDPDSI3. This compound crystallizing the aluminum boron to derive the hexagonal structure, because the compound its crystal structure is same as MgB2, which is a very famous high temperature superconductor. And I show you the crystal structure here. This crystal structure contains here the boron layer, and then you have aluminum layer, and then your bottom aluminum. Therefore, all the layers are alternating here. So in this kind of crystal structure, if you replace boron on the opposite side, and the hexagon here, to replace boron here, you can actually replace an ordered manner. Therefore, you end up with two sides for rare instead of only one side. So, and we have plenty of compounds are known in the structure. Unfortunately, this family was not studied. You can create a ternary compounds out of a binary material. I'm showing this example of palladium to silicon 3 rare silicon crystal structure along the C-axis. This is the hexagon which I already mentioned here. These are all silicon here, and you have the palladium here. And then this palladium silicon layer, as I already mentioned here, is sandwiched by the direct layer here. This is a due along C-axis. This is shown in another form here. This palladium silicon layer. Blue is palladium, and red is silicon here, and the green is rare earth here. You could see these layers alternate here. We basically a triangular lattice here. Therefore, there's enough scope for the magnetic frustration, geometrically frustrated magnetism. This material, we have published about 50 papers in this family till now. Published in physical review letters, physical review B, bringing out all kinds of anomalies due to magnetic frustration in this family. Okay, this another view that along C-axis is basically a honeycomb structure. You could say there are two different sites for rare earth we are getting. Okay, now the first paper on this family was published by 1990 by a chemist, and there is there you know the data, except they report very preliminary magnetization data from which can basically determine only the magnetic moment. So we have studied this family, entire family, very exhaustively, both on polycrystal and single crystal, using a variety of experimental techniques. Now, this I show, since I decided to stick to gadolinium to palladium silicon to a large extent, I used to brief the data here. This is susceptibility as function of temperature. This is your inverse susceptibility is essentially linear, Curie-wise behavior, and where theta of P is positive. If theta of P is positive, that implies there is a strong ferromagnetic correlation. Our system undergoes magnetic or antiferromagnetic ordering at low temperature. Sorry, my cursor is not working well. Antiferromagnetic ordering here at this something like 21 Kelvin. So we did also mass bar spectroscopy in Berlin. When I visited there, you could see very clear evidence for the loss of magnetic hyperfrequency around 21 Kelvin. This established that this compound orders magnetically at 21 Kelvin. So now, on this, though theta is positive, it orders antiferromagnetically, and that means a strong competition between ferromagnetic and antiferromagnetic interaction in this material. And when we measured the AC susceptibility, look for spin loss. There is no evidence for spin loss in this material. This raises the question: what is happening to the competition between these? Now we look at electrical transport. This is one of the probably the most important figure. This is the data which I presented in 1998 at a conference in honor of Professor Joshi. Therefore, I'll spend a few minutes on this. The electrical resistivity not as function of temperature. Look at these. I measured as function of yttrium composition, diluted the gadolinium sublattice. This is the minimum, very well-defined minimum here you could see. This is a positive temperature coefficient paramagnetic state. This, however, below something like 40, 45 Kelvin, there's an upturn here. There's a magnetic ordering at this temperature 21 Kelvin. This is very, very surprising. And then when you dilute by yttrium, even then the minimum is still there. And you could see here, sorry. Sorry, my cursor is okay. So the minimum minimum still persists even when you have only 20% of gadolinium here. Is this typically what is in Kondo lattice? In Kondo system, you dilute, you take a Kondo lattice, cerium compound Kondo lattice, dilute it, you will keep seeing the minimum here. So, and then you measure heat capacity in the above the magnetic ordering, a very huge tail, and even if you dilute, the tail still persists. This all suggests is behaving like almost like a heavy fermion. And then I measure magnetite resistance, the minimum is suppressed here. You see a positive temperature coefficient. If you look at the magnetite resistance value, they're quite large, which you really don't expect for simple metal of this kind. Therefore, you give this transparency to anybody working in the field of Kondo lattices or electron correlation, you would say you are taking gadolinium, you have taken cerium. You have made a wrong sample. So in fact, I sent it to PRL. PRL referee says the results cannot be correct. Therefore, you rejected the paper. And then I sent the paper in Europe's letter. Those say Europe's letter was supposed to be on par with PRL. And then referee responded after 3 months. He responded back saying that I repeated experimental data. The results are corrected. Very surprising. Published it. The referee went to the extent of repeating the results that he did not believe the data. So anyway, this is the most exciting data. I would say even today is exciting data. In fact, S.K. Joshi came and spoke to me on what could be various possibilities on this. And of course, he came out with his own ideas at that time, little more informative to me. So this is one of the most exciting findings, in my opinion, in conductor physics we have never seen in the past. In a simple material, and this comes only before magnetic ordering. Instantly, it is not due to any just lattice disorder. Because I show you, we have studied many materials, and this comes only before the onset of magnetic order. It is magnetism related. I will produce more proof on that. Anyway, since the referees raised the doubt on the sample, and we also measured on single crystal, you could see the minimum persists even on the single crystal in this material before the magnetic ordering persists. Similar magnetic resistance here. So this clearly suggests the data is quite genuine. We published in 1999 in Physical Review B on that. And then we found subsequently, we have this is one of the activities which we are carrying out apart from other phenomena. Let's take simple material and try to see whether there are any anomalies in transport properties or other properties. And we found there are many other materials of that kind. But in GW copper germanium 3, there is a minimum here, which can be a little bit suppressed, and GW-PT-Si3, again the one more minimum. This crystal structure is same as that, same as the gadolinium silicon 3. This another crystal structure, the layered compound. Even here you find a minimum here. There are some more compounds. Macro is quite large, though you don't see minimum here. So there is an additional contribution coming up in this family. Subsequently, by the way, even for arsenides, very famous, we studied good number of arsenides. And this is another arsenide with a layered structure. We published it on PRL, not only on gadolinium. Almost all the members of the family, barring cerium and praseodymium. In cerium, praseodymium, you find a very huge upturn before magnetic ordering. If the magnetic ordering temperature is this, you see a very huge upturn here. You could see not only gadolinium, also dysprosium, terbium, also samarium, everywhere. So this seems to be quite common, except people have not noticed it. And we analyze the data in whether it's electron localization is possible or whether there is any Kondo effect. We try to do analysis. No explanation, no known explanation could really explain this data. With this data, this paper was published just like that in Physical Review without much problem. Okay, so now there are other families. I mean, there are rarest rhodium 3. Look at the cerium. This is there. You don't see minimum here. The temperature resistivity is positive here. There's a magnetic ordering here. Even neodymium, you don't find it. When you got heavier errors, look at it. There is a very temperature resistivity is positive, negative here. This is very surprising. The light errors you don't find. However, in the middle of the error series, you find that negative temperature resistivity. Very, very surprising. And then if you look at these, of course, you have more complicated behavior, transport behavior, low temperature because of magnetic superzone formation. And let me go to one example, GD7 rhodium 3, tell you it's truly magnetic. If you plot magnetic resistance as a function of magnetization square, you will find that in the paramagnetic state, all the lines are falling one over there. There is very beautiful scaling between magnetization, magnetoresistance in the paramagnetic state, right up to 300 Kelvin. Values are reasonably large. You don't have 300 Kelvin, anything more than 0.5%. Still, a very for room temperature, quite a large value. This establishes that magnetism is responsible for the paramagnetic transport anomaly in gadolinium and these materials. Now, since dysprosium rhodium 3, there is another maximum here. You could see similar behavior, a very huge anomaly here, and it could be suppressed by the magnetic field. Right? This is even almost up to room temperature. And again, there's a very scaling between magnetization. This one, again, terbium 5 silicon 3, you could see right from room temperature, you could see the negative temperature under resistivity here. Sorry, this one here. And this is a magnetic ordering at this temperature. So it's a completely different structure here. There is no frustration with material. Recently, I published a paper along with my postdoc Ram Kumar and Karthik and others. The resistivity minimum also persists many other components, GD4 PTAL, Also, terbium for PTAL, you could see the minimum does not even go by the application of magnetic field. You carry very huge field. In one compound, terbium to PTAL, minimum is absent in zero field, however it appears in applying magnetic field. This is again very funny. Why does it appear in terms of magnetic field? So therefore, you could see in the paramagnetic state, you see all kinds of transport behavior. The basic message I'm trying to drive on the basis of the transport data in the paramagnetic, I'm not sticking to paramagnetic state, is that in some normal rare earth metallic materials, there's an additional T-dependent contribution resistivity as magnetic orderings approach, sometimes leading to contour like minimum. This was not never realized in solid state physics. So I'll come back now. This question was never addressed, and of course I talked some theoreticians and recently there is an attempt by Batista, one of the very young theoreticians, is working in all kinds of on materials. I was suddenly one fine morning contacted me that they happened to look at our paper, and we have some theory for that. He got some more details from me about the crystal structure and other things. They come out of the idea that in the event you have a triangular lattice and there is an antiferromagnetic interaction, which I show here, that people in the audience will know the triangular lattice here, and there is an intrinsic frustration, it's called geometrical frustration. This frustration combined with the Roorkee interaction in metal can give us an upturn at low temperature before system orders magnetically. So, and then he says, we could look at the reference list here. I don't know, read the first paragraph. They were motivated by our experimental results. Here, they have cited 3 papers which published PRL and also in EPL and other journals. They are motivated by results. Subsequently, there was some more work recently by Los Alamos group. They come out with some system with similar behavior, which he also cited here. And therefore, he said must be some general problem in solid state physics. They come out with what they claim the first theory to explain the resistivity minimum in such materials. And then recently there's another paper in physical B, and they diluted it. Remember, I already mentioned, even when we dilute the minimum crystal flexes, they come out with a theory to explain the dilute limit. And of course, they called that, you could see the plenty of reference. All our papers have been cited, and they claim that they are motivated by our own results. And it is possible in the dilute limit, you see, we don't require concentrated limit. Okay, now I finished the results in the paramagnetic part. Let me see. This is compound also very exotic. Even the magnetic ordered state. I'm going to magnetic ordered state. Even the magnetic ordered state is a very exotic transport anomaly which was not known earlier. Now it is attracting a lot of attention in the literature. As I already mentioned that this susceptibility data and AC and DC both have shown there is a competition. You have both ferromagnetic and antiferromagnetic interaction here. However, there is no spin loss behavior. We raise the question, there is an interesting competition here in this material at that point of time. And if you look at isothermal entropy change from Maxwell's equation of use in the magnetic data, you derive it, also heat capacity. There are all the sign reversals in the delta S here, you could see here, plus and minus. This also tells you there is both anti-ferro and ferromagnetic interaction across the material. So therefore, and then we measure Hall effect, and you will find that there is a sign reversal here. All values are quite huge. Now, there are initial indicators suggest that both antiferro and ferromagnetic correlations are present. Now, we measure Hall effect on single crystal. We saw something very, very exotic which was not known earlier. And first of all, magnetization, you see the 2 metamagnetic transitions here. Magnetization as function of field, there are 2 transitions here. Now, across these 2 transitions, you see a magnetic resistance drop, a very huge value here. Now, we measure Hall effect on this. This is what is very surprising. If you measure Hall resistance as a function of field, it goes up at the first measurement transition field and drops at second measurement transition field. And look at the value, it's very, very large. I mean, people who do Hall measurements will know that you don't expect 2 micron centimeter in this magnetic order. Normally, nano-ohm centimeter, very, very huge. We raise question, values are large. There's a maximum, and not only that, this law which is mentioned is breaking down here. The Hall resistivity is a function of normal resistivity and the anomalous resistivity due to magnetism. And this law is breaking down. As per the law, we plot rho m as function of h, rho h as function of h. Both curves should look similar. They are not looking similar. We claim there is a very interesting magnetic structure in this material. We published a paper physically B in 2000. at that point. We left it at that stage and bringing out various features, also even the transport in the magnetic ordered state. Now, recently, there's a paper by Tokras group. They picked up our results, and of course, they say that here they cite our paper. Only the citation is not proper. They say these people have published transport results. They found interesting transport data. They left it like that. They measured again Hall effect, now which is now called topological Hall effect, and they find skyrmion. I will credit them for finding skyrmion behavior in this material by resonance scattering measurement. Okay, this therefore the intermediate field, gives enhanced Hall effect, which is now called topological Hall effect. As all of you know, topological Hall effect was for the first time experimentally recognized in magnetic materials in manganese silicon and iron cobalt silicon 2009. This was 10 years after we produced these results, and that time the concept of topological Hall effect did not exist. When we said that it's a very complicated magnetic structure, these authors find the skyrmion lattice, and we are very pleased. However, I mean, the fact that we measured Hall effect was not explicitly mentioned in our paper. Look at the Hall data here. Hall resistivity is exactly the same as what we have reported in our paper here. So this is a topological Hall effect, which is now very well recognized in current literature. And the science editor has clearly written down here that this paper was detected through transport measurements in magnetic field, that is Hall effect. So it's very pleasing for us to see that something which existed 20 years ago, Tokras picked up and brought it out to limelight. Of course, now attribution skyrmion lattice. Now I wrote to science editor, and of course I written those interested can see in Conmat article. I written up the also a science e-letter that brings out this was done actually 2 decades ago. Now the same Matissa's group of on the same material G2P3, which they have now these are I think anyway in general community ignores. This is the only group which has taken note of our Hall data, and they cite this here. They explain the giant topological Hall response G2P3 1011 reference our work, and they come out with a theory to sort of how the skyrmion crystal can be formed from optic interaction and magnetical ordered state. So this is quite satisfying. So at least somebody has taken note of this. This paper was published in Physical Review Letters. And there is, I just want to inform the audience that recently in another paper, we found similar behavior, same as G2PDSI3 in another family, rhodium silicon 3. All the properties are similar, except we are yet to measure all data. And the material we are going to measure on that. So there are, what I want to say, there are many families of compounds showing very interesting transport behavior, not only in the parameters, also in the magnetic ordered state. Though this paper has been published very recently, 2020, in Physical Review B. Okay, the take-home message I would like to say is that I don't know how much time I have. I just want to tell that though I would have talked about various other subjects, we have exotic results on magnetodielectric coupling, also heavy fermion, other things. I decided to talk about it mainly because to pay my homage to Professor Joshi, who really got excited with this data. And we have more data on this subsequently. Some other groups also brought out similar anomalies from Las Lamas group. The basic message is that even those materials like gadolinium, terbium, etc., other heavy rare earths, I didn't brief them here. I did not have time. This you find even terbium and dysprosium also. We have published quite a good number of papers. Even the so-called normal rare earths, which were traditionally considered uninteresting, they show normal properties, not only in the magnetic order state, also in the paramagnetic state, which is very, very important, particularly transport behavior. Kondo-like upturned metals need not be due to Kondo effect. The new theory for triangular lattice emerged very recently, but there is no universal explanation because we found also in other structures where you do not have magnetic frustration. And we think that more than one theory is really required. The problem is still open. And kindly allow me to not to be modest. I generally try to be modest. I don't want to be modest now because some people like Tokara picked up our results. We have done a pioneering work in this direction, leading to novel concepts and novel magnetic states in the current literature. We reported Hall anomalies even 2 decades ago, even before the concept of topological effect was known in 2009. So thank you very much. That's all I want to say.
Thank you, Sampath. Thank you very much. I think this paper has done, your talk has done 2 things. One is to remember Professor Joshi. Another is to remind people that the area of rare earth magnetic metallic systems contains all kinds of mysteries which are even now not fully understood and therefore, I believe that if there are people who are interested in asking questions, maybe they should ask.
Professor Supath, I am Devakant here from Institute of Physics. It was excellent talk. I just wanted to know that part I could not get clear. In your high temperature phase, paramagnetic phase, there's too much difference in the zero field resistance, and when you apply magnetic field, there is too much magnetic resistance in the paramagnetic state that you showed in your initial slides. I think that you attributed somewhere one theoretical paper to this antiferromagnetic triangular antiferromagnetic structure. But that still I could not understand why it will give that antiferromagnetic structure. If that is the case, is it generic? If other materials have this kind of antiferromagnetically triangular structure, do you also expect in the paramagnetic state such a large this magnetic resistance?
Maybe probably you're not understood. See, this is still paramagnetic. This is still paramagnetic. There is no antiferromagnetic structure. Because I think there is no antiferromagnetic structure. The antiferromagnetic interaction in the triangular lattice between two different sides. See, if you have antiferromagnetic interaction between two different sides, the third side gets frustrated. It's called geometrically frustrated magnet. It is geometrically frustrated lattice. Therefore, if you have such a lattice and you invoke RKKY, the theory predicts that you can in principle see an upturn. That is basically a substance. Therefore, the theories focus mainly on triangular lattices. But as I already mentioned, we also in the layered structure, there are compounds where you don't have triangular lattice. There also we find, and nobody knows what the origin is.
Okay, thank you very much.
Yeah.
Thank you. Anyone else would like to ask something? Maybe I can ask two things. One is, you see, one of the slides you showed seems to actually show giant negative magnetoresistance. The magnetoresistance is enormous and it is negative. Now, of course, there is a whole family of systems called colossal magnetoresistance systems which show that. I don't know whether there's any similarity between the two. This brings me to the next question. You see, if there is to be a universality in this phenomenon, it has to reside in each gadolinium ion. So is it then that the magnetic structure, I know it has many F electrons, then there is a crystal field, and therefore the magnetic moment is arranged in a certain way. The electrons are arranged in a certain way, and so on. So, is there any work on trying to connect the observed anomalies in almost all gadolinium systems with some atomic properties of gadolinium in these crystal lattices?
Okay, a very good question. And I just want to tell you there is no correlation between what is in CMR and this gadolinium emitter. The reason CMR, you, for example, you can double exchange. Here only RKKY, the 4f electron is strictly localized. And the only commonality is that I already given on transparency that the magnetoresistance tracks magnetization. The plot is universal plot. That is the only, it comes from magnet. That is very, very clear. It comes from magnet. That is the only commonality. Mechanisms are different. Now, coming to second question, that we already shown that the same GDT is said to be diluted. Even the dilute limit, we are seeing it. I think I already shown on transparency. Even the dilute limit, we are seeing it. And the theory paper, which of the group of Batista, they predict it's a single ion property. Basically, they claim the single ion property. And of course, we have studied at least one system, two system dilute limit. And we do find it in the dilute limit. Yeah. So therefore, it is not a lattice phenomenon. It is basically also a single ion. It appears to be a single ion phenomenon, very close single ion limit. Yeah.
Very good. Thanks very much. Is there anyone else who would like? I actually believe that there are a lot of mysteries which are not solved, and maybe 20 years later they will be reproduced with another set of ideas and phrases. But it is very good to remind ourselves that from 1999, 1998 to now, the mysteries have actually mostly remained. Thank you very much.
Okay. Thank you.
I would actually now like to ask Professor Bhanu Mahanti, SD Mahanti, to share his impressions of Professor Joshi.
I have to see, I have disconnected before that.
Yeah, please do, please do.
Sorry, I have to cross that. What do I do? Disconnect it, stop video? No, sorry, no.
No, you're done.
I'm done.
Yeah.
Your slides are disconnected. I hope you are not disconnected.
Sure.
Can I be heard? Everybody can hear me from here?
Yes, we can.
Right.
Okay, I don't have any slide to share, only my memories to share. So it is first thing, let me thank Devakant, Swankar, and so on for asking me to be a part of this. But besides celebrating Joshiji, it's great to see all the old friends. TVR, old days, so I haven't seen him. Arghya, TVR, Sampath, Didi, and young students. I think Tulika is here, and many others. Anyway, nice to see you. I am now trapped to my son's home, one room, one corner. I don't have access to the office. So I'm in California now. So I'll take some time to talk about Joshiji. And now that I'm in Los Angeles, Riverside is not too far. So it brings back many memories of my interaction with Joshiji. I was to bring him to show him, what is that place? You show everybody, all the guests, Disneyland. So, but anyway, let me start out a little bit about history. I came to Allahabad University in '61. You know, those days after coming from Orissa, which is a sort of so-called, used to be called backward and so on, we used to come to do PhD in Delhi University. So that's what my aim was, and Delhi University wanted to, everybody was going there to do particle physics. And in fact, one of my very close classmates came there, and I could not get admission to Delhi University because I was slightly younger in age. There was a minimum age. So I didn't want to go back to Orissa, so that was the first accident. What else one can do? There is Allahabad University, which is very well known. A lot of people from Orissa used to come to study there and get into IAS. But I was not interested in that. I wanted to do physics. I came to Allahabad, drove from Delhi to Allahabad. Actually, we drove from Calcutta to Delhi. I didn't get admission, came back to Allahabad, and I joined Allahabad University. And that's how an accident, because of that accident, I came to know Joshiji. So Joshiji was, as Professor Ramakrishna said, he was finished, I think he finished his PhD with Dr. Banerjee doing X-ray diffraction. And and we had to choose some special topics. So I chose X-ray. And I think I was in his laboratory, and he taught us how to take X-ray diffraction, do all the experiments. He didn't teach me, but now that you mentioned, I remember very well two things. And this is going to be anecdotal and mostly he said he was doing experiments, but he somehow got interested in doing lattice dynamics. I remember Allahabad University, we had a big sort of a corridor, veranda. Outside, evening, I would see Joshiji used to come, big notebooks, and writing down 20 by 20, 30 by 30 matrices, trying to work out the lattice dynamics phonon frequencies. And amazing, I mean, he was all the time. We used to go to play cricket, come back, and Joshiji was there in that office. And that I can see why, he produced so many very original work in those days in lattice dynamics. Not too many people were doing such calculations. And he was very much interested in fitting to the experiment. That was the main focus. I mean, there were formal theories developed, but he was trying to fit the experiments. So that was one real memory I have. The other one is very interesting. This will be young students, you might know, you might like. You do final exam, you give final exam, there is a practical exam. And Joshi was our internal, somebody from outside came. And we were in his class, there were 5 or 6 experiments you do, Lave pattern, this, that, crystal structure. So you do your lab work, and in the lab note, you score your nice picture. So that's you submit it. Then the external examiner came, and we did our experiments. Then it was found that from everybody's lab book, all the pictures were gone. The pictures were taken before, very good photographs of X-ray patterns. They're all somebody had taken away. And so the question was, who did it? And this brings back to Joshi as a human being. And he was in charge, so he sat in a room and called each of us, one of us each at a time, asked, what happened, where is your notebook, why did, what happened to your picture and this, that, and so on. In the end, it turned out, it's a sad story, but one of our students, what he did before the exams, he went to went through all the lab notebooks of all the students, picked away all the pictures, took out the figures, kept it, hoping that whatever experiment he gets, he would put that one. Anyway, he found a person, but clearly he would have been thrown away, fired, and so on. But Joshi somehow told us, let's give him benefit of doubt. And in the end, he was allowed to take the exam. I think he passed it. Of course, he became a good physicist later. But it was a kind of Joshi, he's coming from Pahad. He was an extremely nice person. And so he sort of saved that person. I'm sure he saved his scientific life. And that person became later a well-known dean and so on in the Indian science system. Anyway, so that was the end. So I left Allahabad, and things should have been different. I somehow came to University of California, Riverside to do PhD with Professor T.P. Das. He was visiting Orissa. He gave me an assistantship. I came away, right, 64. And then that would have been end. But interestingly, in 64, I think, Das was visiting Allahabad University. Maybe they were trying to hire him as a professor. Joshi had met him. And then in 65, Joshi came to Riverside. Dr. Das went on a sabbatical. So they had to have a replacement, and Joshi came. So it was one of the great time in my life. And that's how when I came to know Joshi really very well. He came to Riverside and had fresh year doing lattice dynamics, and came to Riverside. And he had just married, didn't know how to drive. And Professor Das left for England in sabbatical. So I was Professor Das's student and one of his good students. So, and from Orissa. So he asked me to stay in his house with Joshi. Joshi and Bhaviji, Mrs. I think Hema, his name, Bhaviji and I shared the house, and we had a lot of interactions, science, non-science. I taught him driving and so on, but 2 or 3 things come to my memory. And as you said, Joshi is a completely self-taught. He did X-ray diffraction. I don't think he had any, he took classes. He did very well, but then he was teaching quantum mechanics. Quantum mechanics is a tough subject to teach. And I had taken quantum mechanics the previous year. I used to solve the problems. As you go to, in USA, as you know, you have to solve all the homework problems, which I did. So every night before the class, Joshi and I would sit down in Professor Das's office, and we used to go through all the quantum mechanics problems. And during that time, we used to talk about physics. He used to ask my research, and amazingly, he did not know much about what in fact, this Archie-Keva interactions and so on I was working on. He did not know, but he would come with amazingly good idea suggestions. And I could see that characteristics of Joshi much later in life. I'll tell you a little bit, one or two more stories. But the next interesting story was, I think TVR might remember. In fact, I also remember those days. I think TVR 70, you had come to San Diego which year to Seoul? Which year did you come to San Diego?
68 to 70.
See, yeah, exactly, 68 to 70. So 68, I had just left. But then you were in New York that time. He was finishing.
Columbia, right.
Yeah, you see. But in 66, 65, Joshiji came. And so he taught. Then 65, Rajagopal. There is another very famous physicist. Maybe some of you know. His name is A.K. Rajagopal. He came from Bangalore, went to do PhD in Harvard, an extremely good mathematical physicist. So, and then he did his PhD with Harvey Brooks on spin density waves and so on. And those were the days of Green's functions, many-body theories, which he learned, came as a young assistant professor. And so he and Joshiji became very close friends. And amazingly, Joshiji did so much work being in India on lattice dynamics, and he was invited to write this famous review article in solid state physics. And not too many people from India had written articles. I think T.P. Das wrote one, and Joshiji was asked to write. Rajagopal was not. So Joshiji came, and Rajagopal had come, joined. So we were all together at that time. Joshiji came and asked Rajagopal that, Rajagopal told Joshiji that, he has been doing lattice dynamics using more fancy many-body theory. That time from Harvard School, this functional derivative techniques, swinger techniques had come out. Gordon Boehm and Karanov were sort of pioneers. Rajagopal had learned all the techniques, and he was so good, he could derive everything without seeing anything. So he told Joshiji that how about adding to this review article a many-body formulation, a Green's function formulation of the lattice dynamics. So Joshiji didn't know anything about many-body physics of the Green's functions and so on. So then the first thing, he was a little bit worried, but then what he said, okay, let's write to Seitz, who was the editor. And Seitz somehow they had a very strong, he said, okay, why don't you add that as a second part to the review article? And if you read that article, that is very disconnect. One is experimental, parametric, other one is highly very, very mathematical formulation to Green's function. But they were together. And what is interesting is I was taking a class from Rajagopal trying to learn. So and the night, Joshiji and I used to derive some of the equations what Rajagopal was doing. Anyway, that was a good learning period with Rajagopal and Joshiji. That was a very good period. I asked Rajagopal to write something. He wrote up, and he said, he told this story, and then, of course, the review article was not submitted. Joshiji became somehow the very famous, just finishing up to 2 years. He was offered professorship in Roorkee. And also, if I remember, I don't train memory, I'm old now. While in transit, he got this Waterman Award given to physicists who had produced outstanding work being in India. Anyway, that was sort of a turning point in Joshi's life. And he came to Roorkee. Rajagopal went to Tata Institute, TIFR. Then they met together, worked on that review article, and then that paper was published in, the article came in 69. It's one of the classic papers, and Joshi is one of the major contributions to the field. But so that was the Riverside period. And plus, I had a lot of nice things to memory, but let's not worry. But what is interesting, Joshiji was aware of many things in a lot of seminars. And those times the disorder systems were coming in. People were talking about Kondo effect and Hubbard model, all sorts of things. And somehow Joshiji was going to seminar, was observing, because when he came back to Roorkee, and when I came and saw him in 71, he had, I don't know, 10 students. Each one is working on, one was working on Hubbard model, one was on CPA, one was looking at some very interesting problem, Kondo effect. So Joshiji somehow that TVR you showed why he was working so much, because he was simultaneously learning a lot of physics during his period at Roorkee, I'm sure. He organized conferences. I remember one of my colleagues, Gabor Kemeny, came to a conference in, I don't know, 68, 69 on strongly correlated system in Roorkee University. So when things were, not too many body theorists from USA like TVR, Krishnamurti, they had not come back. So Joshi had come and thought that would be an interesting field to work on electronic structure. And I don't know whether he did DFT calculations or not that time, because we were doing DFT calculations in 66, 67 or 68, I don't remember. But so Joshi's way of doing science was extremely student oriented, talk to people. Maybe later it went into experiments, and he was a very fast learner. And that reminds me a story. Whenever you give a seminar, Joshi will be there. In the end, he will summarize your talk way better than you talked. So he will give the perfect basic understanding of your lecture. This is what Bhanu told, this. I said, yes, Joshi, that is exactly what I meant to, but perhaps I did not convey. So that was my first period of Joshiji, and then we became very good friends. I used to go visit him anytime I'm in India. Then he was one more encounter, and then I will finish. That when everybody was trying to go back, I think TVR had gone back, and I also wanted to go back to India. And Joshiji was very kind, and that time in Orissa, they had started the Institute of Physics, and condensed matter physics was not in vogue those days, but somehow they offered me a job. I did go, but somehow I couldn't stay because of some personal family problems or something. But he was trying to bring people, help them, develop groups, and that's how he helped, I think, create Indian science. And that I could see him later when I was old. I could, part of some committees, Joshi will sit, let everybody talk. In the end, he will summarize very nicely who said what, and he perhaps made the right decision. And I think we will all miss him as a person. And science, of course, was part of his life, and his memory will be there. And just to finalize, I got an email yesterday from Sushanta Dattagupta, perhaps most of you know, and he had just mentioned that he wrote a small article about Indians' condensed matter physics, and he gives a lot of credit in Indian condensed matter physics to Joshiji, and of course world condensed matter physics to Professor Anderson, and who coined that word and contributed tremendously to that field, made that field, if you think that way, modern condensed matter physics. And Joshiji plays a very important role in doing that in Indian science. Anyway, thank you for listening, and that's all I could remember. I'm getting old. I may not have any more memory. Thank you. TVR, yours.
Yeah. It was from the heart.
Yeah.
Wonderful. Thanks very much.
Little bit from the brain, but heart. Yeah.
No, it's very good. Very good. Thank you. Is there anyone who wants to add to it? Because I think Bhanu knows him the closest and longest among all of us. It would be nice if someone has something else to say also. Maybe at the end of all this, we will have someone. At the moment, we will have... tell me. What?
No, you are right. So you have memories, different memories, positive, negative. But another interesting story I forgot. Once I was on my way to Bhubaneswar. I was sitting in Delhi airport waiting for the plane. Here, early morning, 6 o'clock, I see a known person walking back and forth at the airport. So I followed, looked like Joshiji. I said, Joshiji, yes, I'm going to a committee meeting in Bangalore, in Madras, Chennai. I'll go in the morning, come back. And we're just chatting here at half an hour. So that time, NISER, National Institute of Science in Bhubaneswar, had come up. So he said, Bhanu, things are going well, but somehow one particular department is not doing well. What can I do? And that was math department. I said, Joshiji, math is physics is different than math. Math need culture, and and maybe you should somehow hook up the nicer people to TIFR math or something, so that some exchange will give them some push. But he was always thinking about things, about institutes. He created so many, and so many people in their head. So he was always thinking about things. Yeah.
Thanks very much. Yeah. Could I request Professor A.V. Mahajan to talk?
Yeah, thank you, Professor Ramkrishnan. So it was, of course, nice to hear reminiscences from Professor TVR, Professor Mahanti, and also Sampath about Professor Joshi's contribution to Indian science, how he has been an institution builder and also a big figure in Indian physics. I of course, I did not have the good fortune to have any interactions with him. However, as it turns out, I had interactions with some faculty members of IIT Roorkee in various inter-IIT sort of some programs. And so I remember Professor Ishwar Singh Tyagi and also Professor Ajay, who is going to speak a couple of talks later. They always spoke very highly of Professor Joshi, and I remember especially Professor Tyagi talking about the very vibrant and very lively atmosphere in the physics department when Professor Joshi was there, and motivating everybody in the department to do new things and also imparting all his wisdom. So that's about as far as my interaction in a second order manner was. It's interesting, Professor Mohanty was talking about T.P. Das. So I work in NMR. T.P. Das is a very well-known figure. He's a very big review and monograph also associated with nuclear magnetic resonance. And there also I had the good fortune that in a very old March meeting when I was a PhD student, so I gave one of those contributed 10-minute talks, and Professor T.P. Das was the chairman of that session. So, there also I have a very short few minutes interaction with Professor T.P. Das. So anyway, this is, so I'm not exactly connected with Professor Joshi's work, but this is what I have based on my interactions with other people from IIT Roorkee. So as far as this talk for this session is concerned, let me just go ahead and try to share my slide. Yeah, so this should be coming up now. So let me go to slide share mode. Yeah, and maybe sometimes it helps to have a pointer. So let me have a pointer. After Sampath talked about intermetallics, I'm now moving over to oxides. Sampath did mention that, even 20 years back, they worked on various interesting systems, and similarly in the intermetallic variety, but even in oxides, he worked some time back on triangular systems. And of course, these are of current interest now. He gave a very short message about the frustration that is present in triangular systems. So in this talk, I'm going to talk about one such spin half triangular system based on copper. And this is our recent work where we show that in spite of strong antiferro interactions between the copper ions in this material, down to the lowest temperature, this system does not order, and it seems to show gapless excitation, so a gapless quantum spin liquid behavior. I should warn for some of the people in the audience that this is one talk I've given before, so kindly pardon me for that. Next time you see me, maybe I'll present something new. Okay. Incidentally, the work that I'm presenting here is largely the work of my former PhD student Sushant Kundu and also associated postdoc who was working with me at that time. And the theoretical support is by two people. So Sumiran Pujari is a fellow faculty at IIT Bombay, and Indra Dasgupta is also the next speaker at ISCS. So he and his student Atashi worked out density functional theory calculations. And some of the low temperature measurements, also the ESR measurements were done at Michel Bennett's lab, some by Sushanto when he was visiting there for a couple of months. And I'll also present MUSR measurements where we had a couple of days of beam time at ICES, and Pavitra Biswas and Mark Telling were the local help at that point when we went and did the experiment there. Certainly funding and facilities by both DST, IIT Bombay have to be acknowledged in this. So what is our interest? What is the motivation in going to this oxide? So a couple of years back, there was already some work on a copper-based system with a triangular lattice with this sort of chemical formula, Ba3CuSb2O9. So these are essentially of the triple perovskite-like variety. So you can imagine copper and Sb, if they were in the same ion, then it is it's in these metal ions are in the ratio 3:3 and oxygen 9. So this is of the kind AbX3 3 times. And so many of the oxides of current interest have their origins in either a spinel lattice or a perovskite lattice and so forth. So this one really has an origin in the perovskite lattice. And the interest here was that in spite of, again, this is looking at copper, and it's very much a triangular lattice that is present. And these people found a spin liquid state for this material. And so that got a lot of attention. So basically you have copper 2 plus ions in a triangular plane. And then along the C-axis, they apparently are not well connected. And so that probably promotes this 2D behavior and eventually a quantum spin liquid. Well, it turns out, so there are interesting features in the heat capacity, some linear term and so forth. As you would expect for a fermion case. So these have been dubbed as like a spin-on Fermi surface in these. So these are insulating systems. And so there's interest in such behavior of bulk property. Well, it turned out later that this is not as simple as it looks. There are different structures that are present. And so even then, there are still novel features. So you have these Cu and Sb dumbbells, and you could have them ordered or disordered. So it could go into a honeycomb or a triangular geometry. But nevertheless, in various kinds of geometry, they still showed interesting ground state properties and also low energy excitation. Even replacing the spin half with a spin 1 nickel also gave very interesting properties. So at that point, we were wondering whether we introduce chemical pressure by replacing the barium ion by the much smaller strontium ion, and whether this replacement would give rise to perhaps whether the structure remains, crystal structure remains the same, or it changes. How does that impact the magnetic properties and so forth? It turns out it was also possible to replace the Sb, which is non-magnetic 5+, by Nb, niobium 5+, because of the very similar ionic radii. And it turned out that there was no report on the magnetic properties of the strontium analog. It's still copper spin half system. So with this sort of motivation, we worked on the strontium copper antimony oxide system and also the niobium. I'll present here data associated with the antimony based system. So the basic introduction to magnetic frustration is contained in this slide. As Sampath already mentioned, that if you have Ising spins on a triangular motif, there is this associated geometric frustration because you cannot satisfy all the spin interactions simultaneously. And then what does happen when these are there in actual real material? That has been an interesting question. So this is stated by Anderson long ago. And the RBB has perhaps the origins in this kind of frustration. So eventually it turns out that the edge-shared triangular lattice appears to have ordered 120-degree oriented spins as the ground state. However, there is still interest in this various triangular system because you might have other important interactions also, which prevent this kind of 120-degree ordering. So going from a edge-shared triangular lattice, one can go to a corner-shared triangular lattice, which is even more frustrated, and so there is a significant amount of work on that. One can move on into 3 dimensions where you have now corner-shared triangles. You can have corner-shared tetrahedra. So there are these various geometrically frustrated systems where you'd be interested in looking at what the ground state properties are and whether it's really actually obtained in a real system. So what would you look for in experiments for something like this? Well, what is typically looked at, and this, these criteria have evolved over the years as theorists have given us more and more inputs about what to look for. So to start with, one early on, maybe 10, 12 years back, one said, okay, you just look for the bulk susceptibility as a function of temperature. Look if it has a Curie-wise behavior with a negative theta, so suggesting antiferro interactions between the magnetic moments, and look whether there is any evidence of long-range ordering through a sharp peak in the susceptibility, etc., whatever temperature. So if not, then maybe you have a significant region in this temperature range where you expect spin liquid type properties. So you have local moments which interact antiferromagnetically very strongly, but somehow magnetic ordering is disallowed because of some fundamentals of the geometry. And one frustration parameter was also defined, which is the ratio of the antiferromagnetic Curie-wise to the actual ordering temperature if it exists. And one said, oh, if this parameter is high, then this is a strongly frustrated system. What is very high, it's not so clear, maybe 100,000. So it depends on the system. Okay, but clearly, again, anecdotally and just based on thumb rule, a frustration parameter of 5 or 10 is not so significant because it doesn't allow you for much range where you explore the spin liquid behavior. On the other hand, if it is much larger, like 100, or if you don't even see ordering, then that is quite significant. Then over the years, theorists told us, oh, this is actually an entangled state. You should also see fractionalized excitation. So now people are looking at these kind of excitations in various experimental techniques like inelastic neutron scattering and so forth. Nowadays also thermopower, also looking for entropy changes, etc., which might harbor evidence of fractionalized excitation. So, the field is evolving, and then we are learning from experiments as well as theorists on what to look for, whether something means there is frustration or not, and so forth. Many examples by now for these systems, some are noted here. I'll just go over to what we have done, and what I'm going to present here is a subset of that. So we prepared polycrystalline samples of the strontium copper antimony oxide, but also the niobium, which goes into a same structure and seems to have similar properties. There's a comprehensive series of measurements on this, supported by theory also. So there is a clear synthesis and characterization by X-ray diffraction and refinement. Also bulk probes of magnetization and heat capacity, and local probes of ESR, MuSR, and NMR on these. And theoretical support from Indra and Sumiran, where there's an ab initio calculation of various exchange parameters, and explanation of this based on a Dirac spin liquid phenomenology by Sumiran. So to start with, the underlying structure for this system is really the ABX3 cubic perovskite structure. However, what we have here, so just on the face of it, the cubic perovskite structure is not geometrically frustrated. It does not apparently have any triangular sort of motifs. However, in the present case, the B site, you have talking about SR3 Cu. So the B site is populated by Cu and Sb. And because the Cu and Sb ions are quite different in ionic size, it turns out that one can get this 1:2 cation site ordering at the B site. So in a crystal structure, if you have copper occupying one side next to by Sb, copper, Sb, Sb, etc., And then one has the site ordering, and then one can get a triangular geometry if one looks at the 1-1-1 plates. Okay. In the usual disordered situation, there is no triangular geometry, but in the if you look at the pseudo-cubic lattice, then one can get a triangular geometry in the 1-1-1 planes. And actually, we have evidence from superlattice peaks in the X-ray diffraction of this 1-2 cation ordering at the B side from copper and antimony. So the only magnetic atom here is spin equal to half copper. Okay, so here is just a sort of quick snapshot of the X-ray diffraction pattern. It turns out finally the structure is tetragonal because these various metal oxygen octahedra, in order to sort of match them, keep them in the structure, they tend to rotate and tilt and so forth. So the symmetry is disturbed. It goes away from the cubic and then settles in a tetragonal symmetry. So one can index all the peaks in the X-ray diffraction pattern based on that. But in addition, in the small angle region shown here, just below 30° 2 theta, one has some additional peaks, and it turns out you can index them based on a 1/3, 1/3, 1/3 superlattice propagation vector. Okay, so one establishes that there is a CU-SB site ordering, and in that case, as I showed in the earlier figure, the 1-1-1 planes harbor the triangular geometry. Now, if you look at the bulk properties, which we come to shortly, so this is again a caricature of the triangular planes. So we are looking at this ABC lattice parameters, and then these marked red lines here suggest interactions between the nearest neighbor copper. And they are also shown in the figure on the right, where you have the J1, which is the nearest neighbor copper-copper coupling, and then the J2, which is the next nearest neighbor within the plane. And then there's a possibility of interplanar coupling through these J2 perpendicular, etc. Okay, so these are the parameters which ab initio will evaluate based on finding the overlap integrals and so forth. Okay, we measured the bulk properties. So here I'll just present a subset of that. So, theorists told us look for Curie-wise behavior. So here is susceptibility as a function of temperature. And indeed, high temperature, it fits well to a Curie-wise behavior with a negative theta, okay, about 140 K. The Curie constant is good for a typical spin-half system. Also, one verifies at low fields. One can verify at, say, 50 Ersed, look for a zero field cooled variation in the susceptibility. So one typically expects in the case of frozen moments or spin glass behavior that you get a bifurcation in the susceptibility as a function of temperature for the ZFC and FC. So one gets some history dependence. So clearly that is not present here. One gets a total overlap of the data for ZFC, FC. If one looks at the AC susceptibility, essentially in low field, so small amplitude of the AC field, there's really no telltale feature, okay, as a function of frequency, as a function of temperature, there's nothing happening. One just sees a Curie kind of behavior. So there is clearly no evidence of any freezing or any kind of ordering. Okay, so first criterion is met in bulk probe. You have a strong antiferro interaction, but no evidence of long range order or even any kind of spin glass order. Okay, then since we suggested that it could be a triangular geometry, so there is a old paper by Essner, Singh and Young where they model the triangular lattice antiferromagnet, and based on Pade approximant, they give an expression that you might expect for the specific heat as well as the susceptibility as a function of temperature for a triangular lattice antiferromagnet with only nearest neighbor interaction. So based on this input, we draw here the solid curve here, which is for a triangular lattice with the nearest neighbor interaction of 70 K. The discrepancy at lower temperatures is not abnormal. One often has orphan spins in these systems, and at low temperature, because of the 1/T Curie behavior, they really overwhelm the data. And so one could still have a triangular lattice behavior, and maybe at lower temperatures, other interactions or parasitic spins or some other features that come in. So this is the situation up to now, that there is no sign of ordering There's a suggestion of triangular lattice antiferromagnet interactions being present. Okay, then the local probe that we encounter here is a muon spin resonance, where you do the experiments, do various kinds of experiments. Here I show the experiments in zero field. Again, to give a quick, very quick introduction, what is done in muon spin rotation, muon spin relaxation, is that muons which have a magnetic moment, you shoot them at the sample and you implant them inside. And then these muons are sensitive to what are the local moment dynamics within the sample. Okay, and then you detect the muon has some lifetime, it decays in some 2.2 microseconds, it gives off a positron. So based on the detection of positrons and what their angle dependence is, how quickly they relax and so forth, we obtain information about what the local moments are within the chemical system that we are investigating. So muon is a probe of local moment dynamics within your sample. And it's a very sensitive probe. Also, it's a zero field measurement. So it's really probing the ground state. So what is shown here is something called the muon asymmetry as a function of time. And this is done at various temperatures. So muon is very sensitive to what is happening inside. It's also sensitive to the nuclear moments. Here, of course, you have copper and antimony nuclear moments also present. It's sensitive to those also. The characteristic behavior because of interaction with nuclear moments, which are really paramagnetic all the way, is different from interaction with local moments from the electron. Okay, so the high temperature behavior here, high temperature is 4K or so. High temperature behavior is characteristic of relaxation due to nuclear moments. So this muons are relaxing, they are getting depolarized. As you implant them, they are fully polarized because that's how they are produced. And as a function of time, because of the local environment inside, they get depolarized, they lose their magnetic polarization. Here, in the high temperature, due to nuclear moments, but as you come down in temperature, they get relaxed because of the electron moments, so the copper moments in this case. And based on this, you can obtain some kind of relaxation rate for these muons. Okay, so that relaxation rate, so to cut out all the detailed analysis here, one finally obtains based on the exponential relaxation of the muon depolarization as a function of temperature. One obtains this lambda muon relaxation rate as a function of temperature. And one sees that there is a slowing down. So one sees a relaxation rate increasing, but then it levels off at low temperature. So once again, there is no telltale sharp peak in the relaxation rate, which would be expected for long-range ordering. Also, there is no decrease to very low values if you had static moments at low temperature. So these basically show that you have magnetic moments and they remain dynamic down to lowest temperatures in spite of strong antiferro interaction. Okay, so the lowest temperature is 65 milli-K. You compare that with the exchange coupling, which is of the order of 70 Kelvin. Okay, the other aspect one looks at is how easily you can decouple these magnetic moments from the internal field by applying an external field. So one applies an external longitudinal field and sees how you can now, so if the external longitudinal field is strong, then of course the muon will remain polarized, okay, because of the external field. So the internal field will not be able to depolarize it. But if the moments are dynamic, then typically it is known it is hard to depolarize these muons. So here that is what is seen at the low temperature of 90 millikelvin. Even in a 2000 Ørsted field, the local moments, the muon polarization is not lost. You get significant muon polarization, muon depolarization as a function of time. The other point is, when you now try to fit this, you find that this is depolarization is happening because of electron dynamics, electron moment dynamics. So if you normally just assume that the electron autocorrelation varies just exponentially as e to the minus nu t, where nu is just the frequency, fluctuation frequency of local moments, then it doesn't fit the data well. Okay, one needs to take another tau by t to the power x in the correlation electron autocorrelation function in order to fit these lambda as a function of magnetic field, magnetic field variation of the electron relaxation. And this is again considered an evidence of temporal correlations being present even when there is no static order. Okay, so both these are hallmarks of quantum spin liquid. Okay, the other piece of evidence is from a bulk measurement, which is the magnetic heat capacity. So one measures the total heat capacity, and one wants to extract the magnetic heat capacity out of that. So one has to somehow subtract out the lattice part. There might also be a Schottky term because of some two-level features in the system, because there are some free spins present. So generally, it's not very straightforward to extract the magnetic heat capacity. However, fortunately, in this low temperature region, the lattice part is really, really negligible. And if there's any magnetic part, it stands out. Okay, so one also needs to take care of the Schottky anomaly. So it was possible for us, we found that if you now focus on the low temperature region, so this shows the measured heat capacity as a function of temperature, and this is shown on a log-log scale here. It was possible to fit the measured heat capacity as a combination of a linear, quadratic, and a Schottky term. There's also a cubic term present because of the lattice part. However, in this low temperature region, especially below 2K or so, it is utterly negligible. And if you don't even consider this, one doesn't get much different values of the coefficients gamma and alpha. So the significant result here is that one could fit the measured heat capacity as a combination of a linear term, like you would expect in a normal metal, fermion-like term, a linear term, a quadratic term, and then the Schottky term is also here extrinsic. Okay, so essentially the magnetic heat capacity appears to have a combination of a linear and quadratic term. Okay, and then Sumiran, based on Dirac spin liquid formalism, could work out the variation of heat capacity with temperature as coming from a quadratic and the linear term, and based on the coefficients here and comparing with our experimental data, the gamma and the alpha from the experiment, and comparing with the expected coefficients of the t-square and the linear term, actually we get a number for the J over KB, the prominent coupling in the system, about 50K. Okay, note that our experimental number based on the bulk susceptibility is also about that, about 70K. Then, in addition to this, DFT estimation of the exchange parameters also gives a similar number. So everything from two kinds of theory and experiment seem to be consistently explaining this based on exchange coupling of the order of 50K between the nearest neighbors. DFT also gives a small coupling between the next nearest neighbors, either within the plane or between the planes. And so that explains the essential 2D nature of this system. So based on these, we suggest that you have a triangular lattice system, and perhaps there is importance of further interactions. So this is already suggested in some of the papers that were published earlier. So in a triangular lattice, there's a possibility of a ring exchange being present, and that might drive this kind of spin liquid behavior. This is another one where they're looking at not only the nearest neighbor, but further neighbor interaction, which can give rise to such spin liquid behavior. There is another possibility of a J1, J2 Heisenberg model. So J2 is the next nearest neighbor. This is another one by Yasser Iqbal and people, where again they're looking at a J1, J2 triangular antiferromagnet. So presence of the nearest neighbor as well as the next nearest neighbor in the otherwise uniform chain. And in both these, they expect some spin liquid behavior in some parameter space of J2 by J1. So, it's quite possible that you have other interactions present in this system, which go beyond the simple nearest neighbor J. And that drives the spin liquid behavior. The key feature here is that one sees gapless excitation. There's no exponential reduction observed in the susceptibility or the heat capacity, but rather a quadratic variation of the heat capacity. And this arises from Dirac cones, which are present in the band structure of this material. So with this, I'll just put up the conclusion slide where we have looked at strontium copper antimony oxide, which is found to be different from the barium-based system in that the structure is different and apparently has no triangular planes. However, because of the CU-SB site ordering, one does see triangular planes if one considers the 111 pseudo-cubic. In the pseudo-cubic cell, if one looks at the 111 plane, one does see a triangular lattice. And based on various bulk and local probes, there is a clear evidence of the absence of a long-range order. And this is supported by DSL phenomenology, which gives an exchange coupling of 50K, and also by density functional theory, which gives nearest neighbor coupling, the dominant coupling of, again, similar order. So overall, our results indicate gapless quantum spin liquid behavior, so with linear dispersion in this spin half system. And results were recently published in PRL, which is given here. So thank you for your attention. And of course, I'll be happy to answer questions if any.
Thank you, Professor Mahajan. I think there should be or there will be questions. I already see a hands up. So let me start. Yes, please. Go ahead.
Sampath here. Okay, Mahajan, you gave a nice presentation, very neat data. But I mean, permit me to be a little mischievous, if you don't mind.
Sure.
Okay. I misuse your friendship with you. See, you said that there's an ordered replacement of copper and antimony. Okay, you also see superstructure in your analysis, I think XRD. So, but is it uniform throughout the sample? Maybe you will see some ordered, some part may not be ordered in another part because of so this is number one question. A related question is that because we are disorder, if you have that kind of disorder, partly ordered, partly disordered, if you look at heat capacity, if you see, I see very prominent T cube term. The T cube term can also come from antiferromagnetic component. Not necessarily that spot.
Yeah. So
a small part. Okay.
Yeah. I'll respond to a few of the things.
Okay. Comment. Everything related.
Yeah.
Now you look at gamma. You are saying gapless. You attribute gapless spin liquid, but gamma, if you have spin glass, also you have a finite value. So therefore, I wonder. I think what I wonder, if you argue against that, it's only for like an argument. I mean, I'm not right. You may be right, but there could be a disorder which leads to partly spin glass, partly antiferromagnet. Everything. What is the mixed data? So, what's your response to that?
So, firstly, there is definitely no spin glass behavior. Our lowest temperature is 65 millikelvin with an exchange coupling of the order of 140K. So in MuSR, down to 65 millikelvin, there is no chance of any spin glass behavior. At least down to 2K, this is also clear in the AC susceptibility or low field ZFCFC of the DC. The other point is, if things are non-uniform, then usually you should get frozen magnetism, which is clearly not present. So other data which I did not present. So although polycrystalline, we could do transmission electron microscopy on some particles. And there you see, so we could get nanocrystals, and there you could see clear spots and also superlattice spots because of this ordering, even in the TEM pictures. Okay, so spin glass is quite ruled out. And about the T cube term, actually, as I said, the T cube term is absolutely negligible. So from the high temperature heat capacity, if you extract a beta, that matches with what you expect for the lattice, and then you use that for your low temperature fields. There is no additional T cube. Okay, and so you really have only gamma T plus alpha T square. The T square arises from the Dirac spin excitation. Application of a field gives rise to the gamma T term, and the values are also in agreement with the Dirac spin liquid terminology. So I don't know if that answers some of your question, but you can please go ahead.
We can discuss it later.
Yeah.
Anyway, nice presentation. Thanks.
Yeah, Yogesh, please.
Yeah. Hi, Avinash. Very good talk. I learned a lot. So I just had a material curiosity. You tried to connect with some ring exchange models, and that happens when there is some charge fluctuation. So what is the charge gap here for your material? Have you estimated?
No, not estimated, but these are well insulating. So
Very insulating, right?
Yeah.
Right. Okay. So, and my second thing is that this DSL, is it true for any triangular lattice, or what are the recipes where you expect DSL kind of spin liquid?
So Sumiran is the right guy to ask this question.
Okay.
So,
right. Okay. So I'll catch him then. Right.
Sure.
Thank you.
Yeah, I had a similar question. You see, the two questions. This Dirac spin liquid. Maybe I should ask someone else, but you tell me. The Dirac spin liquid means what? The excitation spectrum of there are some spin-ons whose excitation spectrum is Dirac-like, or the electrons themselves have a Dirac-like excitation spectrum, or what?
So yeah, my view is these are spin-ons which have a linear dispersion. So that's what. So it's the spin-ons which have this Dirac-like excitation.
Okay. Then the other thing is that I guess that in these geometrically frustrated systems, there is no possibility of a Kitaev-like interaction.
Right. With the copper only, so purely spin-based moment. Right. Yeah, I guess there is not. Yeah.
Okay. Good. Yeah. Let's go ahead. Right. Thanks. Is there anyone else who would like to ask?
Yeah. May I just interject this, DD? Avinash, with respect to the question that Sampath asked about the ordering, Rietveld analysis, the superlattice peak intensity is related to the extent of ordering. So do you get 100% ordering or close to 100%, which would imply then it cannot be described as some parts being disordered, some parts being ordered?
Yeah, the intensities actually match. In the Rietveld, they match 100%.
Which means that it's 100% ordered, essentially nearly. So that would answer the question that Sampath was raising.
Yeah. So, however, this is still from a powder sample, so I would not go so far. However, there is no evidence of glassy behavior. That is sure.
Hello. Thank you very much. Then, if there are no more questions, I would like to go on to request Professor Indra Dasgupta to give his talk.
Thank you, Professor Ramakrishnan. Am I audible?
Yeah, audible and visible to me.
Okay, good. So I'll just like to share my screen. Is the screen visible?
Yes, we can see it.
Okay, thank you. Is it fine now? Is it in full screen mode? If somebody can
yes.
Okay. So I first begin thanking the organizers, and I'm really honored that I'm speaking in a session dedicated to Professor S.K. Joshi. So I belong to a generation of physicists where I really did not get a chance to interact with him academically, but I happened to meet him. The reason being that he happened to be our council chairman during a period when I just joined Indian Association for the Cultivation of Science. And I, of course, heard a lot about him from my supervisor, late Professor Abhijit Mukherjee, who, when decided to come back to India, first joined Roorkee, his group, as a research associate, I think a Silver Jubilee Fellow of CSR before he moved to IIT Kanpur. And the impression that I got for him that he had a vibrating group doing all kinds of, tackling all kinds of problems in condensed matter physics. Later, of course, I met many of his associates and students who were my teachers, and some of them have been Professor Deepak Kumar and Professor Shushil Aulak and my teacher in IIT Kanpur, Rajendra Prasad. So they all essentially gave me a kind of flavor of Professor Joshi's greatness in building a very active condensed matter group in India. So today I'm going to talk about something which is tailoring spin textures in a class of systems called Rashfa systems. And I also saw the web page of this meeting where I found a message by Rashfa. So I thought it would be possibly apt to talk a little bit of Rashfa systems on which we are doing some work. Well, so first, let me begin. So this work has been basically done by two of my graduate students, Shubhadeep Bandyopadhyay, who is about to submit his thesis. So he basically did all the work from ideas to implementation, and what I'm doing here is basically talking. And he was also helped by one of my former graduate student, Atanu Pal, who is right now a postdoc in Bar Ilan University in Israel. And these two work recently appeared in this two PhysRep B paper. Well, so why Rashfa systems?
Hello.
Hello, just a minute. I think I tried to do something and okay. Well, so spin orbit coupling, I think last 5, 7, 10 years have brought in a new paradigm in quantum matter or quantum condensed matter physics. So, and it has essentially added a new axis, which is the spin orbit axis. We are all familiar with this strong correlation axis, and these are the two terms of this generic model Hamiltonian, where you have this hopping and this Hubbard U. And this is the line along which we moved a lot when we tried to understand how the high TC cuprates. And when U is strong, we go ahead and have this traditional Mott insulators, and doped Mott insulators are yet to be understood and are believed to be the systems which give rise to high temperature superconductivity. But as I said, that last 5 to 7 years, there has been another axis which has been added, which is the spin orbit coupling axis. And this axis has been brought into existence by the discovery of topological insulators. So the spin orbit coupling with which we are familiar with is the radial field of the nucleus in a solid, which when seen from the rest frame of the electron appears as a magnetic field. And this magnetic field interacts with the spin of the electrons, and this gives rise to the spin orbit coupling. And then that, for example, leads to band inversion, which is a key ingredient for getting topological insulators. Another area, now, of course, today's talk will essentially be confined to the strong spin orbit coupling, but of a different kind of spin orbit interaction, not resulting from the radial electric field provided by the electron, but for example, a field which is perpendicular along the z-axis, which I'll say as I move along. But what has been also very important has been a region out here where you have a competition between the Hubbard interaction and the spin orbit coupling. This, for example, does what? It, for example, adds a piece to our generic Heisenberg Hamiltonian, the half filling limit, and this is what the Kitaev term or bond dependent exchange interactions. And this bond independent exchange interactions has exciting properties, and quantum spin liquid, which Avinash talked about in the last talk, you can have now what are known as spin orbital liquids, right? Because of an interplay of strong Hubbard interaction and lambda. This is the area on which we have worked a lot in the recent times, but today I'm essentially going to confine myself to a regime where lambda is strong and Coulomb correlations are not that strong. So, I mean, I can basically use a kind of an effective theory to take care of the Coulomb correlations. Well, so with this, as I was trying to say, that spin orbit coupling has led to variety of emergent phenomena, right, which ranges from spin Hall effect to spin transistor, spin orbit qubits, spin orbit torques on one side. You have quantum spin Hall effect, topological insulators, genesis of Majorana fermions, and so on. Well, so the kind of spin orbit coupling that we'll be interested today are what are known as Rashfa, or more precisely Rashfa Dresselhaus spin orbit coupling. So let me go ahead and tell you what Rashfa spin orbit coupling is all about. So Rashfa spin orbit coupling essentially refers to momentum dependent splitting of spin polarized bands in non-centrosymmetric systems. So you have to have a system which essentially has to break inversion symmetry. So what you have here, so in a system, if you have a crystal inversion symmetry and time reversal symmetry, then you have what is known as Squamous degeneracy. As a consequence, your upspin bands are completely degenerate with your downspin band. And this is, for example, if you do a DFT calculation, a non-spin polarized DFT calculations, you precisely get this. Well, if you apply a magnetic field, what the magnetic field does, the magnetic field essentially breaks time reversal symmetry. And then, of course, you essentially start having a distinction between your upspin bands and downspin bands, which is due to your Zeeman splitting, right? So this is what it shows. But you can also break the Squamous degeneracy by breaking inversion symmetry. And how inversion symmetry can be broken? By applying an external electric field. If you essentially break your inversion symmetry by applying an external electric field, then you essentially have a K-dependent splitting of the spin degenerate bands, and these are essentially referred to as Rashfa splitting. Well, so this is the spin orbit coupling that we'll be interested in the present talk as we move along. So as I was trying to tell, absence of inversion symmetry essentially creates a potential gradient from a charged nucleus, which generates an electric field. So now this electric field, right, seen from the rest frame of an electron, right, essentially manifests itself as a magnetic field. And this magnetic field couples with the spin of the electron, right? And what you have, you essentially have now a K-dependent magnetic field. So what you can assume in a real system that this electric field which appears here because of broken inversion symmetry is along the Z direction. And then you can essentially substitute it here and you can recover what is known as the Rashfa Hamiltonian, which has this specific form. I will talk about this Rashfa Hamiltonian and the related Hamiltonian, which is known as a Dresselhaus Hamiltonian as I move along. But this is an electric field which is arising due to a potential gradient because of inversion symmetry. So this is something which one should distinguish, and not from the radial electric field of a nuclei, right? So this is an important thing which need to be distinguished, and this has the celebrated name, which is this Rashfa spin orbit coupling. So what you have essentially done, you have essentially converted your electric field into a K-dependent magnetic field, and of course, this gives rise to splitting of your upspin and downspin band, and this splitting is proportional to K to linear order. It can also have higher order terms, but the first order is proportional to linear order. And because of the spin orbital locking, as I'll show you, this also shows an exciting kind of spin textures, and which plays an important role in making devices. So one of the devices which people thought about is, for example, the spin field effect transistor. So what you have, you have a source where you have spin, which is made of ferromagnet or a half metal. You have a collector, which is also made of a ferromagnet and half metal. Then what you are essentially doing, electrons of single spin from such a system are injected out here, right? And then what you do, you apply an electric field, and now because of this Rashfa effect, which essentially gives rise to a texture.
Sir. Okay.
Is it okay? Am I audible?
Yeah, you're fine. It's
okay,
fine.
because I mean, I could hear some background noise, so I got a bit confused. Okay, so once you apply the electric field, we can essentially tune the spins, right? And they will be delivered to the collector, provided they are aligned with the spin of the collector. Otherwise, they will not be delivered to the collector. And this essentially gives rise to a transistor action upon application of an electric field instead of a magnetic field out here, right? And so this the concept, right, which was devised in 1990, right, about 20 years ago, and still, of course, have to be realized, but where Rashfa effect essentially plays a very important role. The same thing is also people have been looking at Rashfa effects in topological insulators, again with the idea in mind that we can go ahead and manipulate spins by application of an electric field. Well, so let me go ahead and try to tell. So this is what is the, as I showed you, the Raspberry Hamiltonian has this, linear Raspberry Hamiltonian has this particular form, and the form for the Dresselhaus Hamiltonian, you have a plus sign out here. They have similar eigenvalues, which I can show you out here. So these are the similar eigenvalues, the band split. But what they differ, the difference between them essentially manifests in the spin texture. So what is spin texture? You take the Pauli spin operator and calculate the expectation value of the Pauli spin operators, right, with the eigenvalues of the either Rashfa Hamiltonian or of the Dresselhaus Hamiltonian. And then what you get here, if you go ahead and plot them, you get here what are known as chiral spin textures, and which are different for the Rashfa and for the Dresselhaus spin orbit coupling. And as I told you, this momentum dependent spin orbit coupling, which gives rise to chiral spin textures, are crucial for their application or spin manipulation in Rashfa systems. Well, so as I was trying to tell you, that if you choose a system where the electric field is along the z direction, then what you have a linear Rashba Dresselhaus sock, and the most general Hamiltonian can be written the way it is written out here. This is what the most general Rashba Dresselhaus Hamiltonian, and a alpha minus beta of this Hamiltonian essentially gives you the Rashba parameter, and alpha plus beta parameter essentially gives you the Dresselhaus parameter. And a system usually can have both finite alpha and beta, and as a consequence, it can have partially Rashba kind of coupling, partially Dresselhaus kind of coupling, and depending on the system, either of them can dominate. Right? For example, what I've shown here, when alpha is equal to 0.5 and beta is equal to minus 0.5, then your Rashba effect dominates and your spin texture is chiral, which is a specific characteristic of a Rashba spin orbit coupling. But when alpha is equal to 0.5 and beta is equal to 0.5, what you have Dresselhaus spin texture, and you can see this is very distinct from your Rashba spin texture. But you can also have a situation where your alpha is equal to 1 and beta equal to 0, which implies that you have an equal mixture of alpha R and alpha D, or your alpha equal to 0 or beta equal to 1, or where alpha R is equal to minus 0.5 and alpha D is equal to 0.5. And these are what are known as persistent spin textures. So what are they? So they don't have chirality. So they are uniform spin configurations in K space, and they are very important. And people are essentially looking for materials, right, where you can have persistent spin textures or uniform spin textures in K space. Why you want to have them? Because persistent spin textures are robust against spin-dependent disorder, and which can lead to very large spin lifetime necessary for applications. So the question is how one can go ahead and design such persistent pin helix or persistent pin textures. Of course, one has to try with having your alpha R equal to alpha D. And for example, this has been possible in LaAlO3 and strontium titanate interfaces, right, along 001 upon application of strain, right? But of course, managing and maintaining it becomes very different or very difficult. So what people have also argued, certain materials, if you go ahead and look at the symmetry, particularly non-symmorphic symmetry in certain bulk systems, then one can go ahead and stabilize such persistent spin textures. So what I'm going to tell you today is that under what circumstances you go ahead and have Rashba or Dresselhaus kind of spin textures, and what you need to do from symmetry wise so that you can go ahead and stabilize persistent spin textures. Well, so the first thing is that, of course, we have to search for Rashba systems. As I told you, that one of the key ingredients for Rashba systems is that they have to break inversion symmetry, right? And we would like to look for Rashba effect in bulk systems. And one of the key material for such systems can be ferroelectric materials. Ferroelectric materials are intrinsically insulating, and not only intrinsically insulating, they have to break inversion symmetry. So you essentially have this criteria for to sustain Rashba effect essentially getting satisfied for ferroelectric systems. Well, so we are going to look for ferroelectric systems where, because of this broken inversion symmetry, you are going to have the possibility of Rashba Dresselhaus spin splitting. And of course, ferroelectric system where one of the ingredient is a heavy material, because you would also like the relativistic effect to dominate to see this spin orbit effect. The most important thing is that upon application of an electric field, you can essentially reverse the electric polarization, right, or ferroelectric polarization. So this also essentially, if Rashba effect could be realized in such a system, then upon an application of electric field, you can essentially reverse the spin texture. So this is an important thing which one need to keep in mind, that if I'm able to discover Rashfa effect in ferroelectric materials, right, the spin textures could be reversed upon an application of an electric field. Well, so what we have done, we have essentially considered 3 theoretically predicted ferroelectric systems, right? So they have perovskite-like structure, but one of the key ingredients of the symmetry is that all these 3 systems are non-symmorphic, because there has been an argument in the literature that non-symmorphic systems can give you a large Rashfa or large Dresselhaus splitting. So we essentially chosen that. And all these 3 systems, they have the calculated ferroelectric polarization turns out to be 20 microcoulomb per centimeter square for this lanthanum tungsten nitride. It turns out to be 33.6 microcoulomb per centimeter square for bismuth indium oxide, and for Ag2BiO3, which also happens to be a charge order insulator, it turns out to be 8.8 microcoulomb per centimeter square. So you can see they have a nearly same, so they have the same point group symmetry, which is C to V, but their non-symmorphic symmetry operations is slightly different, while these are identical for LAWN3 and BiNiO3, but it is different for Ag2BiO3. So to begin with, what I'm going to do, I'm going to take this LAWN3 in its orthorhombic structure, orthorhombic perovskite structure, and show you that it indeed shows Rashfa effect. So how do we do that? So this is LAWN3, right? And as I told you that this shows a ferroelectric polarization, and the direction of ferroelectric polarization is along 001 direction, which is good, which implies that the system has an intrinsic electric field along 001 direction, which also implies that this is an ideal candidate to host Rashfa effect. Well, so with this, what we went ahead, so we went ahead and did what is known as a spin polarized band structure calculation for tungsten, for LAWNi3, lanthanum bands are empty, tungsten bands are empty, nitrogen bands, and what we are essentially going to focus on is the tungsten band, where the spin orbit coupling is expected to be strong. And this is a calculation without spin orbit coupling, and you can see that there is no splitting. But as soon as you switch on spin orbit coupling, right, what you figure out, we figure out that the band starts splitting, right? So particularly, go ahead and see like the points as you move away from the Z point, or as you move away from the gamma point, they start splitting. They don't split along the gamma Z direction. This is because of the reason, because your electric field is along the Z direction, and as a consequence, the magnetic field which is going to get generated because of this in the rest frame of the electron is going to live in the XY plane, so it cannot split anything along the KZ direction. And this is a good observation because it tells us that the spin splitting that you are having is essentially of the Rashfa kind. Well, what you can go ahead and do, you can go ahead and look at the point group symmetry of this guy, and you can essentially find out that both the Rashfa Hamiltonian as well as the Dresselhaus Hamiltonian are invariant under this point group symmetry. So in principle, we expect the presence of both Rashfa effect and Dresselhaus effect, right? And of course, if they are in equal proportion, then of course, we also expect the existence of persistent spin texture. Well, let's see what the story is as we go ahead and do some more calculations. And of course, we have to go ahead and do model calculations. So this is precisely what we have done. So these are, so what we have done, we have essentially looked at the points around the gamma point, right? And we can clearly see that the band splits because of this Rashfa effect or because of this spin orbit effect. And once we go ahead and calculate the spin texture, we figure the spin textures are chiral, characteristic of a Rashfa effect. Well, that's very good. So this is from a full-fledged DFT calculation. We can do slightly better. And of course, as I pointed out from symmetry, there's also a possibility of Dresselhaus effect, but somehow it doesn't get manifest out here. And the reason is why it doesn't get manifest out here. So spin texture has this opposite helicity, characteristic Rashfa effect, no out-of-plane spin component, which implies pure Rashfa effect. Well, to look at it in some more details, what we did, we wrote down a small K.P model Hamiltonian for the system, right? And once you can write down a K.P model Hamiltonian, and you can see the dotted lines in this calculations are your DFT calculations, and the dotted line is your K.P model, which fits excellently with that. And you can go ahead and once you have this model at your disposal, you can go ahead and calculate your Rashfa coefficient and Dresselhaus coefficient. We find for this system, the Rashfa coefficient dominates the Dresselhaus coefficient. As a consequence, you have a typical Pins texture of Rashfa kind. Well, so I'll just touch upon another point in the case space with Z point, where your non-symmorphic operations or non-symmorphic symmetry operations are much more effective, and which gives rise to a larger splitting. And one can go ahead and do that. One can model this, and that's precisely what we have done. So here, for example, again, you have a Rashfa effect, but now this Rashfa effect has a KZ component, right? It's not only confined to the X, but it has a KZ component, which essentially tells us that this non-symmorphic operation, right, orients this Rashfa spin texture in such a way that it has or it picks up this KZ component, and which you can essentially model by bringing this additional term in your model Hamiltonian. Well, so far so good. So what I'm only going to tell you as I move along, that along the Z point, right, the spin texture is of a Rashfa kind with a KZ component, with a large splitting, primarily driven by non-symmorphic operation. But an important thing which I'd like to take you along is the band which splits has a predominant tungsten dx square minus y square character. Well, so this was, of course, a theoretical prediction. And after a paper came out, we saw an experimental report of this system. At least this system has been synthesized. Nobody has measured its ferroelectric polarization. I hope this will be eventually measured, and possibly the prediction of Rashfa effect will be verified in this system. But now what I'm going to do, I'm essentially going to touch upon another compound, which is BiINO3. And what I see out here, for example, if I do the similar calculation and similar thing, right, I find that the spin texture is of a persistent spin texture, right? Again, at the conduction band, again, at the Z point, right? So this, what I do is that I look at the Z point, right? And I look at the spin textures around the Z point. And for this compound, although having the similar symmetry as that of my LANI O3, LAWN3, so it has a different kind of spin texture. But the thing to again point out here, the conduction band which sustains this spin texture has a character of bismuth px and indium s. Well, so this is our final system, again having the same symmetry again. And what I essentially go ahead and do, again, I look at the Z point, and what I figure out for this compound, what we essentially have Dresselhaus spin texture, right? And again, the point which I'm going to point out, if I look at the character of the conduction band, right, the conduction band is out here is of bismuth S and of oxygen PC character. So the point we're just trying to make, that I took three compounds. First one was LAWN3. It shows a Dresselhaus spin orbit coupling, and the primary character of the conduction band which sustained the spin texture was of tungsten dx square minus y square character. We took this compound BiINO3, where we figured out that the character of the band was essentially bismuth S and oxygen PC character, right? And now we have this Ag2BiO3, where we have this oxygen PZ and bismuth S character. Well, so we can see the spin texture for these three compounds are different. Point groups are identical. Space groups are slightly different. So which essentially implies that despite having the same symmetry, particularly LAWN3 and BiINO3 shows different spin textures, which indicates that it's not only non-symmorphic symmetry or the crystal symmetry which decides the spin texture, there must be something else which is doing it. And this is what we emphasize. We have emphasized that for LAWN3, the predominant character had been, the band had been tungsten dx square minus y square. For bismuth indium oxide, it had been bismuth px. On the contrary, for Ag2BiO3 it happened to be bismuth S and oxygen Pz. So these orbital symmetries also have to be taken into account, right, while deriving your so-called K.P model Hamiltonian or analyzing your Rashford-Dresselhaus model Hamiltonian. So one can essentially do a little bit of group theory to understand that. For example, orbitals like S, Pz, x square minus y square, they're invariant under all C2V operations. As a consequence, they can essentially accommodate all the T-spin components, sigma z, sigma y, and sigma x. But as soon as you go ahead and have px orbital, it has no room for sigma z and sigma x component, right? So what one has to do, one has to essentially take this into account while modeling it. And this is precisely what we have done, right? So once we have been studying LAWN3, what was happening is that the symmetry allowed sigma x, sigma y, and sigma z component, right? But for example, when we went ahead and started looking at BiINO3, right, since the orbital character happened to be of px, the sigma x component was no longer allowed, right? And for Ag2BiO3, the symmorphic symmetry operation was such that sigma z component was not allowed. So what you have to do, you have to essentially include the A or have an orbital symmetry adapted K.P model. And once we do that, we have an excellent fit with our full DFT spin orbit coupled calculations. And of course, the next step is to go ahead and look at the spins textures. And we essentially covered Dresselhaus for LAWN3, persistent spins texture for BiINO3, and of course, your Dresselhaus spin texture for Ag2BiO3. So orbital degrees of freedom, right, or orbital degrees of freedom provides a kind of a knob, right, to derive or to obtain a kind of desired spin texture in a material, which in fact we happen to point out for the first time in the literature. So what we try to say, in addition to crystal symmetry, orbital symmetry is important for spin textures in Rashford system. Well, with that, I will conclude. So broken inversion symmetry with soft can produce linear K-dependent splitting of the bands. The value of Rashfa, or I said Dresselhaus splitting, can be controlled by strength of electric field induced by broken inversion symmetry and provides an avenue for manipulations of spin by electric field. But often, Rashfa and Dresselhaus effect has been analyzed only looking at the crystal symmetry, particularly non-symmorphic symmetry. But we would like to point out there's an additional symmetry which also people need to look into account if you're looking for real systems and real materials. This is the orbital symmetry which gives rise to this Rashford-Dresselhaus effect and plays an important role in deciding the spin texture. Well, with this, I thank you all for your attention. And if time permits, I'll be happy to take some questions. Thank you.
Thank you, Professor Gupta. If there are, I would like to invite questions now. If there are any questions, please ask.
Yeah, hello.
Please go ahead.
Yeah, I have one query. Actually, in the case of your system, do you study related to like thickness dependent, because thickness dependent effect? This is my query. Yeah.
What dependent effect? Can you just tell me?
Thickness dependence.
No, so these are all bulk systems. So we did not do anything. So these are, so for example, as you may be aware, the Rashfa discovered this Rashfa effect in interfaces. But what we tried to argue, or what we tried to show, that Rashfa effect can also be seen in bulk systems, in bulk ferroelectric systems. So these are all calculations for bulk systems. So there is no room for thickness dependent studies.
Okay.
Okay. Any other questions? Maybe, yeah, go ahead. Yes. Yeah. Okay. Maybe if there are no other questions, I will interject and ask a few. First is, are there any, I mean, what do you expect to be the experimental manifestations of these magnetic textures?
Well, that's a good question. So Well, so what people have been, as I was trying to tell, is one of the ways people trying to design are what are known as the spin field effect transistors. And that's where the textures are supposed to play a role, because people believe that you are essentially controlling the spin transport by applying an electric field. Right? And here, for example, the spin lifetime is a very important thing. And if the spin texture happens to be a persistent spin texture, then the expectation would be that the spin lifetimes are higher. Right? So these people have seen, for example, I was trying to tell about this LaAlO3 and strontium titanium substrates where people could essentially go ahead and measure the spin lifetimes and find that they seem to be higher, and which confirms that they are sort of having a spin textures which are persistent kind.
Okay, I had another question with just an idle thought. You see, these are obviously have to be, and they are, zero temperature calculations.
Absolutely.
Now, in this system, it seems to me that there are two temperatures which are not very high. One is the ferroelectric transition temperature. I don't know if that is high or not. And the other is the Dresselhaus coupling constant. See, the Dresselhaus coupling constant, the ones you have shown, they always turn out to be of the order of 0.02, 0.015, 0.0. I mean, like room temperature or some sort of number like that. Whereas, of course, the Rashfa coupling constants are much higher, and so one could very easily think of them as being at for that purpose. One could think of the system as being at zero temperature. So, are there any temperature effects one expects?
Well, so as I was trying to tell you, so the main argument that is being presented in this talk are that if you can identify a ferroelectric system, the ferroelectric system, because of this intrinsic lack of inversion symmetry, is supposed to hold either your Rashfa effect or Dresselhaus effect. Right? So the only experimentally realized system till date has been germanium telluride. Right? I exactly don't remember the ferroelectric transition temperature, but it is quite low. I think it is of the order of 20 to 30 Kelvin, the ferroelectric transition temperature. And below the ferroelectric transition temperature, this Rashford splitting has been seen, right? And which is of the order of a similar kind of an order, right? So this is what the thing is. So room temperature effects and so on, of course, will take a long way to go. So this is essentially a concept where one can realize Rashford-Dresselhaus splitting in bulk systems. This is what I would like to say at this point of time. But realizing them at higher temperature, of course, requires larger coupling and so on and so forth. And that, of course, is something which Fisher has to say.
Thank you very much. Thanks very much. I think it's a totally original direction of departure. Now, I request Professor Ajay to give his talk. He also happens to have been personally associated with Professor Joshi. Professor Ajay.
Yes, sir. Go on. So, is it being shared?
Yes, I can see.
So, Professor the TV Ramakrishnan, the chair of this session, and all the other speakers and who are attending this tribute to Professor Joshi. I chosen to be a topic where we have recently basically working on and also make a mark for some publications. It is actually a problem where you are looking at that how superconducting correlation generate or make a magnetic moment on a magnetic impurity or a quantum dot coupled to a superconductor. So it's a very difficult time for me because I had met Professor Joshi last time when he was basically fighting a disease, and he was beard actually, and it was tough time for all of us. I learned a lot under his guidance at National Physical Laboratory, and it was the time when he was completing his DZ CSR tenure, almost 1995 onward. And what I want to basically mention here that a small tribute. This was the lab where I start for Professor Joshi. It was basically DZ wing, room number 250 and 252. There was two adjacent room, and there was two whiteboard, and there is a galaxy of books on many body theory and solid state. And adjacent to this, there was at the time a silicon graphics supercomputer which was procured from US, and it was quite a highly computational facility available in this laboratory. How I basically came across Joshi sir, it was a research problem. My mentor, Professor Tripathi, who has been from the group of Professor B.B. Dev from IIT Kanpur, and also a Allahabad University alumni. He just given me a problem at that time to study the superconducting phase in high TC material, taking d and p orbital overlap, and calculate the transition temperature of the system based on the just like two orbital Anderson model for that. So I stuck upon to calculate that BCS kind of scenario at that time, and there was band was showing superconductivity, that is D band, which is coming from copper D states, and the P, which is the copper oxygen plane band, was hybridizing, and there is a superconductivity only in one band, and there are Coulomb correlation also. So I just was reviewing, and I come across the Kishore and S.K. Joshi 1972, the overlapping ferromagnetism in two-band system, which eventually led him to Bhatnagar Award. And that paper gave me a calculational insight to renormalize the density of state in the two band, in D and S band, that I utilize to calculate a two-dimensional integral into 1D. And that integral at IIT Delhi, there was Mr. Bob, who was having a computational hand. So we both developed the program, and this work was got published in Physical Review B. It was my first paper. And then we extended this work. And when I just was young graduate completing my PhD, visited Institute of Physics, then Director Professor S.N. Behera, working on charge density wave. And then sometime, maybe around 3-week time, I spent it with Professor L.C. Gupta and Vijay Raghavan group at TFR there to have some experimental insight. And because there was the layered theoretical, you can say, input they require. I feel why was the 95 completing? It was early 96. So I visited Professor Joshi lab, and I show my two PRB paper, and then he has given me a small presentation in front of him. This is the site where there was a big office table and chair where Joshi sir used to sit. So he was just coolly sit down and ask me to present what you have done. Then I think he took a decision in an hour that you can join on contact by tomorrow. At that time, the director of National Physical Laboratory was Professor E.S.R. Gopal. So I was given a contact, and I was given the responsibility to handle a DST project as a project scientist, the transport properties of a strongly correlated system where we have developed a theory. And in that theory, it was N. Kumar and Janware work, model for C-axis transport, which was developed there. So I've been fortunate to start my PhD work of Ramkishore and S.K. Joshi of 1972, a highly cited paper, and usually at NPL, the theory group, Ratan Lal, and at that time, Professor Bhaskaran used to visit. He was a postdoc from the group of Phil Anderson, the RBB theory, and Govind, he is also still at heading a group at NPL. He was just 1 year junior to me, and this was actually the starting point. And in a short span of 2.5 years, and then it was the time where most of the was actually basically made. It was the explosion of exam radio, and most of the position was seized. So somehow the project was completing. So I got a position at physics department, where my PhD mentor, Professor Tripathi, was the head of the department. And this was a very 2.5 years, a very transforming time for me, where I have to show among the other colleagues that Sushil Lamba was there, and Professor Ratan Lal was there, and Professor Ramkishore used to visit. So after that, even I had collaboration with Ramkishore on many aspects, more than a dozen papers we have published. So with this starting journey, I have been blessed that today I'm speaking under the chairmanship of Professor T.V. Ramakrishnan also, because today's talk is based on the idea that how superconductivity control the magnetic moment. It is an inverse process, because as of now, the most of the studies are based on how magnetic moment or magnetism kills superconducting state or interplay with the superconductivity. So to look at reverse phenomena, there are many experimental realization and material where we can have just like impurity, can be think of made up of quantum dot, where we can control their energy level, and we have now well-defined BCS superconductors. Of course, there is a normal impurity interactions which was done by Anderson, and a lot of work has already been done for metal. But to see the effect of a superconducting correlation on a impurity or multiple impurity is of still a very paramount importance, as it has very interesting practical applications which are being seen in many experimental results nowadays. So magnetic moment, but condo effect, you have a superconducting lead, which are basically conducting flow of pair. Our just airing and anti-reflection is sort of Josephson effect. So we had started working on just like single impurity Anderson model, where impurity here is a quantum dot, which can have a distinguished energy level, and we can control number of electron on the dot. And we started calculations in many formulas, initially heretofore, infinite use Lie boson, and now we are doing heavy numerical computation on renormalization group and try to go to the quantum Monte Carlo simulation also. This is the work which I'm sharing with you with two of my PhD students. One is Sachin, he may be in the crowd, and his contribution is immense. In a short span of this COVID time, he has implemented the code and stay with me here. And also Tanuj Chamoli, he is a part-time, got a faculty position, and he has also done NRG. And we have been granted a DST SARB core grant on the coupled quantum dot with a superconducting lead. So if you look at such a systems are available, you have carbon nanotubes, the nanowires, carbon-60, you can basically use these in terms of molecules and dots, because the separation of their energy level can be tuned to the level of, say, 1 milli-electron volt and less than 1, where you can take the advantage of a superconducting order parameter, which is of some 0.5 or 0.2 milli-electron volt, and you can see the interaction of dot level close to Fermi level. So here, these are the realized system, which can be think of the energy level and Coulomb interaction, and a term which couple the energy level with the energy states of the superconducting lead and a superconducting order parameter. So as of now, there are, if I summarize what we have to look for, we want to see the superconductivity in a hybrid nanostructure, where two effects actually initially dominate. One is induced pairing, which is a proximity effect because of the significantly large coherence length. And then there are possibility and a clear-cut experimental indication of Sieber-Reznov states. These are the bound states which can carry current, and still the system is coherent. So when you couple a superconductor by a quantum dot, where dot energy level is close to Fermi level, and the rest of the dot level energy is far away, and its energy difference is larger than the superconducting order parameter, you see a very interesting effect. And you see a sort of formation of a singlet doublet transition, which is beyond Kondo effect. And in this regime, the two conceptually different, yet they are quite deeply related, the subgap states and magnetically induced Andrew bound states, where U is larger, slightly larger than superconducting order parameter, can coexist. So other limit, which one of my Syrian colleagues, Sampath, has described for a metal or for a radium kind of structure, they calculated or seen a phenomena of Kondo effect. But this Kondo effect here will be in a limit when temperature, or you can say the superconducting temperature, is larger than Kondo temperature, you have a blockade. And when this temperature of this system is less than the Kondo temperature, then you have singlet formations. So there is a transition from singlet and doublet, which depend on the Coulomb energy coupling of the dot state with the lead, and also the binding energy of the Cooper pair. So this work I have just we have just got published, and before publications there was some questions which was asked by the referee. So I was insisting on WhatsApp with the Professor Ramakrishnan, because I have seen that in one of the paper in 1967, which basically inspired to implement this work on superconducting state, we have seen that RS Tripathi 1967, a two-page physics letter, where there was an acknowledgement to Professor Ramakrishnan for discussion. They obtain actually different result. It was the first paper I've seen in the history where superconductivity is seen to have impact on the magnetic moment, which is basically embedded in a superconducting state through some impurity. So if the first step we have done is actually a mean field study. And this is quite different from the Anderson idea, where they have metal and impurity basically hybridized together, and there are many possibilities in terms of the localized magnetic moment. So here the physics is actually a singlet doublet transition. But if you switch on a superconducting state, there is one more component. There are resonant bound state due to anti-reflections, and at the same time there is a possibility of singlet and doublet phase, and this doublet phase become robust in certain regime. So these spectroscopic scale study compel us to take in limit of a superconducting gap can be taken quite large as comparable to other parameter. And since there are experimental inputs, we initially started with the model which is based on just like your Anderson model coupled with the BCS lead, and we have made a Bogolubov transformations in order to brought the energy scales you can say leveled, and we find that this coupling actually finally we started with u equal to 0, and these results are actually obtained, which hinges on that the density of state actually show you the bound state within the gap region, and these bound states carry current. So you have a Josephson transport here in u equal to 0 limit at low temperature. Total Josephson current actually has two components. One is the Andrew bound state plus continuum. And this Andrew bound state current actually is showing at equilibrium a crossover, or sometime the phase and current characteristics show a discontinuity. And when you plot current versus phase at different energy level, which is in terms of the hybridization, you see oscillations, and the corresponding Andrew bound states are showing you a touch at the zero energy level, which is Fermi energy. And when you have the finite energy level, there is a gap. So we have calculated the current phase characteristic of it, and then we slowly went to U on 0. We have found a result which does occupancy on the dot. If you calculate, show you if the particle solutions, which basically can be different physical states, and started when the energy realm omega, and omega is very, very small superconducting order parameter, a singlet doublet transition, which we have calculated for superconducting system. In superconducting system, for omega less than superconducting order parameter, there is a robust doublet phase which is probable, and singlet phase show a suppression. And this shows that in particular regime, the magnetic moment on the dot is become robust because it support a doublet transition. Beside this, we have also extended this result for finite delta, and a heavy numerical computation was done on MATLAB by taking the self-consistency loop, and these calculations are extended, and we then plotted the magnetization or difference of the magnetic moment as a function of Coulomb energy. And we found that this magnetic moment and the resonance superconducting pairing on the dot has opposite effect. The time the magnetic moment suppress, the resonance of the paired state on the dot start becoming robust. So these are the very interesting result beyond the single impurity Anderson model. which is basically shown a singlet doublet transition as well as a very reverse effect, which is supported by experiments that the superconducting correlations may generate or may make a magnetic moment giant on the dot if it is close to Fermi level. So we have also seen the role of the subgap states, which are formed, and we have seen a transition from singlet to doublet and then singlet state close to the Fermi level with different binding energy, which is equal to the Coulomb energy, and the coupling of the dot and superconducting state is taken to be as gamma. So these doublet singlet transitions is visible, but still there is a Andrew bound states which are coexist with these singlet doublet transition states. So these results are actually qualitatively agreement with the recent experimental data, and also they are primarily the renormalization group approach results. Even the mean field results are capturing some of the highlight for that. So if I just put a summary of the work which we have done and which need to be taken care of is in U tending to 0 and U non-zero regime, the quantum impurity embedded behave differently if you are in a regime in the bound state, and if delta is finite, then there are singlet doublet transition, which is actually beyond the Kondo effect that is seen when the Kondo energy scale is smaller than superconducting order parameter. So this is the regime where we are going away from Kondo effect, and it basically support a doublet phase. So with this, we have tried to convert this result to strong coupling regime and extended the other properties using multiple 2-dot and 3-dot terminals. And there is a very recent experiment where the double dot supercurrent was measured by this Denmark group. And these results are very interesting because these double quantum dots embedded in superconducting lead is an experimental realization of the two impurity Anderson model in superconducting leads. And here the discontinuity in the conductance is seen at certain point. And these discontinuity leads to a 0 pi phase transition. And you can see the doublet here. But whenever there is a transition from singlet to doublet, there is a discontinuity in the conductance. So these results are very interesting, and they are beyond mean field calculations. So we have recently focused on these double quantum dot embedded in superconducting state. We granted a core DST project, and this work I collaborated with the Professor Vidyadhi Raja from Jain SR, one of the pioneer person in NRG from trained group of HR Krishnamurti there. So these results actually compel us to think that the superconducting state actually, when you see its effect on magnetic moment on impurity, and impurity level is close to Fermi level, so there is a tunability of Josephson phase and singlet doublet transition phase, and there is a temperature which has to be scaled with the Kondo temperature, which is actually lower than Kondo temperature. So these applications are actually the basis of superconducting qubit, this one double dot, and Cooper pair splitters, the quantum squids and quantum computing. And we are developing a theoretical background on this. We have also gone to the correlation theory, and currently in the phase to see a non-Kondo and Kondo regime results. And also beyond Hartree-Fock, we have also done the infinite use Le boson approximation by Tanu Chamoli, where we have used the projection operators and then find out the Lagrangian parameter for single dot. And what are the important result here that you can go also to extend it, that even in infinite U approach, the Andrew bound states persist, and they show a clear-cut location within the gap states as a current carrying state. So there is still a coherent transport of the Cooper pair, even you take infinite U limit, and we have plotted the normalized DOST and also calculated the Andrew bound state energy in both the cases. So these results are very, you can say, new findings in these directions based on the right from mean field to finite U to infinite U. And now we are planning to extend these results by using renormalization group approach. And we have implemented it also by using the SQDS for single dot, then Bogoliubov transformation, and then for time reverse pair, we have done unitary transformations. On one side, we have gone through Schrieffer-Wolff, other side through projection operator. And currently, we are in a position to obtain the effective Hamiltonian and implementing the renormalization core. First for small u, which you call as pyramid scaling. And this is our project also, which we are implementing nowadays and a collaboration with JNCSR. So finite U theoretical approach for the two imperative in a BCS effective Hamiltonian is a quite interesting problem. And theoretically, one can brought this problem to analytical regime. And wherever analyticity lost, one can go to computation, just like numerical computation due to renormalization group. So we have done most of the part of it. So it is still under publications. So I will like to summarize here my work that the reverse feature where you take the superconducting state and its effect on the magnetic moment has much more theoretical gap. Even in infinite U, say Hubbard approximations, the result are close to experiments. But to extend it to two impurity, which is serve as a superconducting qubit, you require one of the, you can say, some laborious mathematical steps to come up to the effective Hamiltonian and then do renormalizations. So we are in this process. And I would like to here at the end, or you can say close this talk by a small word, which in a letter, Professor Joshi has basically put inspiration. When I was at Panth University, I was having a period where I was not having some project and there was a lot of teaching load. So I just plead to Joshi sir to give me computational facility. At that time, he was the chairman of DRDO recruitment cell at Timarpur and used to take care of his research at NPL. So he just wrote a letter and underlined, Ajay, handicap compels you to think origin. And then I wrote the project to CSR, DST, visited. He allowed me to visit both the laboratories where computational facilities was there, and still remember his guidance. And we could publish some of the interesting work out of that. And thank you very much.
Are there any questions on Professor Ajay Singh's talk? Well, if they are not, let me thank all of the participants for this unique session, which is a mixture of reminiscences and description of original work directly or indirectly inspired by Professor Joshi. Thank you all very much.
Thank you, sir. Thank you, sir.
Okay, now let's switch on the cameras and we can have a few photographs. I can capture a few images. Switch on your cameras. Just start capturing. Thank you. Still, I think coming up. I should switch on my camera. I forgot to switch on my own. Thank you. Okay, thank you, everyone. Now, on behalf of organizing committee, I would like to thank Professor T.V. Ramakrishnan, all the speakers and participants for this session. And I personally apologize for the confusion in the beginning of this talk. And I again thank Professor T.V. Ramakrishnan. So we will close this session now. And there is another session at 12:30, where there will be 4 contributory talks from the students. And I hope to see you there. So we should encourage the students by participating in this particular session. So I again thank you, everyone. And now I will close the session. Thank you. Thank you, everyone.
Bye, everyone.
Bye.
Thank you.
Thank you. Thank you, everyone.
Bye.
Thank you. Thank you.
Thank you. Goodbye. Bye-bye.